If you like the space and learn about its curiosities, consider subscribing to the channel. Thank you for your attention and enjoy the video. When you look up at the night sky, the stars seem eternal, glowing pinpoints of light suspended in the vast darkness. But every star you see has a story, a beginning that traces back to the most ancient chapter of the universe itself. The formation of stars is not just a celestial process. It is a tale of chaos, order, and transformation that began billions of years ago in the aftermath of the Big Bang. The Big Bang, the moment that brought the universe into existence roughly 13.8 billion years ago, set the stage for everything we know. During those first moments, the cosmos was a soup of energy and fundamental particles, too hot and chaotic for stars to form. But as the universe expanded and cooled, protons and neutrons fused to create the first atomic nuclei, primarily hydrogen and helium. These primordial elements became the building blocks of everything, including stars. Yet, for millions of years after the Big Bang, the universe was a dark and unremarkable void, a time known as the Cosmic Dark Ages. No stars, no galaxies, just vast, invisible clouds of gas and a scattering of dark matter, which interacted gravitationally but emitted no light. It was during this quiet epoch that gravity began its patient work, pulling together clumps of gas into denser regions that would eventually give birth to the first stars. The transformation of these cold, sprawling gas clouds into blazing orbs of light is one of nature's most dramatic alchemical processes. As gravity worked to compress these clouds, pockets of gas began to collapse inward, heating up under the immense pressure. These collapsing regions are what we now call molecular clouds, or stellar nurseries, and they are the cradles of star formation. Imagine vast clouds stretching for hundreds of light years, containing enough material to form thousands or even millions of stars. But why does star formation happen at all? The answer lies in a delicate balance of forces. As gravity pulls gas together, opposing forces like thermal pressure and turbulence resist this compression. Only when gravity becomes strong enough to overcome these opposing forces does the process truly begin. The result is the fragmentation of these clouds into smaller clumps, each destined to become a star. What's fascinating is that these clouds are not uniform. They are riddled with turbulence, creating a chaotic dance of swirling gas. Within this chaos, some regions achieve a higher density than others, becoming the seeds for future stars. These dense regions are like pearls forming inside an oyster, hidden within the turbulent maelstrom. Once a gas cloud begins to collapse, the real magic happens. As the material falls inward, it forms a spinning accretion disk around the central core, funneling gas and dust into what will eventually become a star. This spinning motion is not just a cosmic coincidence, it's a natural consequence of angular momentum. It's the same principle that causes a figure skater to spin faster when they pull their arms in. As the cloud collapses, its rotation speeds up, creating the dynamic, swirling structure we see in star-forming regions. These early stages of star formation are veiled in mystery, quite literally. The dense clouds of gas and dust block visible light, making it impossible for traditional telescopes to peer into the heart of these stellar nurseries. However, advancements in infrared and radio astronomy have given us the tools to penetrate this cosmic fog. Observatories like the James Webb Space Telescope are now unveiling stunning details of these hidden processes, revealing the intricate beauty of star formation. Star formation is not an isolated event. It often occurs in waves, triggered by external forces such as the shockwave from a nearby supernova. These explosions send ripples through space, compressing gas clouds and kickstarting the birth of new stars. It's a cosmic cycle. The death of one star sows the seeds for countless others. The formation of stars is not just a mechanical process, it's a transformative one. The early universe contained only the simplest elements, hydrogen and helium. But within the fiery cores of stars, nuclear fusion began to forge heavier elements like carbon, oxygen, and iron. These elements would later be scattered across the cosmos through supernova explosions, enriching the universe with the building blocks of planets, oceans, and life itself. As we peer deeper into space, we're looking back in time, glimpsing the universe as it was billions of years ago. We see ancient galaxies, some of which contain the very first stars ever formed. These so-called population 3 stars were giants, hundreds of times more massive than our Sun. They lived short, brilliant lives, ending in spectacular explosions that seeded their surroundings with the first heavy elements. Though none of these primordial stars survive today, their legacy is imprinted in the chemical composition of the universe. Even today, the process of star formation continues across the cosmos. In galaxies like the Milky Way, molecular clouds still collapse to form new stars, though the pace is slowed compared to the early universe. In the largest star-forming regions, we see clusters of newborn stars illuminating their surroundings, casting away the darkness and filling the universe with light. The story of star formation is ongoing, an endless dance of creation and destruction that has shaped the cosmos for billions of years. From the primordial hydrogen of the Big Bang to the blazing stars that light up the night sky, the journey of star formation is a testament to the beauty and complexity of the universe. Beneath the glittering expanse of the night sky lie vast, hidden realms where stars are born. These regions, known as star-forming regions or stellar nurseries, are some of the most dynamic and awe-inspiring environments in the universe. To understand how stars come into existence, we must venture deep into these enigmatic pockets of gas and dust, where gravity and physics perform their cosmic ballet. The term stellar nursery might evoke an image of calm and nurturing space, but the reality is far from serene. Star-forming regions are chaotic and tumultuous, marked by swirling clouds of gas, shock waves from dying stars, and the relentless pull of gravity. These regions are dominated by molecular clouds, immense accumulations of gas and dust that span tens to hundreds of light years. Their name reflects their composition. They are primarily made up of molecular hydrogen, the simplest and most abundant molecule in the universe. One of the most iconic star-forming regions visible to us is the Orion Nebula, a sprawling, colorful expanse located just 1,344 light-years away. When viewed through telescopes, it reveals a mesmerizing tapestry of pinks, purples, and blues, painted by the ultraviolet radiation of newly born stars. Yet, these vibrant hues are only the surface of an environment teeming with activity and transformation. The Orion Nebula is a microcosm of the processes that define star formation across the universe. At the heart of any star-forming region lies a complex interplay of forces. Molecular clouds, despite their vastness, are incredibly tenuous, often less dense than the best vacuums humans can create on Earth. Gravity, however, works slowly but persistently, gathering this diffuse material into denser regions. As pockets within the cloud collapse under their own gravity, the process intensifies, setting the stage for the birth of stars. These collapsing pockets, or cores, are where the real action begins. As the core contracts, it heats up, forming what astronomers call a protostar. This stage is like the embryonic phase of a star's life. Protostars are surrounded by an accretion disk, a swirling ring of gas and dust that feeds material into the forming star. These disks are not only crucial for a star's growth, but also serve as the birthplace of planets, moons, and other celestial bodies. Our own solar system began in such a disk about 4.6 billion years ago. What's truly remarkable is that no two star-forming regions are exactly alike. While regions like the Orion Nebula showcase clusters of young stars, others, like the pillars of creation in the Eagle Nebula, highlight the dramatic structures carved by stellar winds and radiation. These towering columns of gas and dust are sculpted by intense ultraviolet light from nearby massive stars. The resulting structures resemble ethereal spires, frozen in time, yet constantly eroding under the relentless energy of their surroundings. Star formation is also heavily influenced by turbulence within molecular clouds. Think of it like weather patterns on a global scale, but spanning light years instead of continents. This turbulence creates dense filaments within the cloud, which often serve as the initial sites for star formation. Recent observations with telescopes like the Atacama Large Millimeter/Submillimeter Array, ALMA, have revealed these filaments in unprecedented detail, showing how they weave through molecular clouds like veins in a leaf. Another crucial element in the anatomy of a star-forming region is the role of feedback. As young stars ignite, they unleash powerful stellar winds and emit copious amounts of ultraviolet radiation. This feedback can disrupt the surrounding gas, halting further star formation in some areas while triggering it in others. The Orion Nebula, for example, is illuminated by a cluster of massive young stars called the Trapezium Cluster, whose energy is shaping the nebula's future. What's extraordinary is the sheer diversity of stars that emerge from these regions. Massive stars, many times the size of our Sun, form in the densest cores and have short but brilliant lives, often ending in supernovae. In contrast, smaller stars like red dwarfs are born more quietly and can shine for billions or even trillions of years. The conditions within a molecular cloud determine not just the number of stars, but also their mass and longevity. Stellar nurseries are also where we find evidence of the universe's past and future. By studying the light emitted from these regions, astronomers can determine their chemical makeup, revealing insights into how previous generations of stars enriched the gas with heavy elements. This cycle of star birth, death, and rebirth is what drives the evolution of galaxies and ensures that the universe remains a dynamic and ever-changing place. Interestingly, not all the material in a star-forming region ends up in stars. A significant fraction is left behind as interstellar dust and gas, which may later form new clouds or remain suspended in the vastness of space. This leftover material, however, plays a critical role in obscuring young stars from our view. Observing these hidden objects requires specialized telescopes capable of detecting infrared or radio wavelengths, which can penetrate the dense shrouds of dust. Some star-forming regions are so massive that they produce clusters of thousands, or even tens of thousands of stars. These clusters, such as the Pleiades or Omega Centauri, provide a snapshot of stellar diversity and allow astronomers to study how stars evolve over time. In the densest clusters, interactions between stars can influence their trajectories, creating a dynamic and unpredictable environment. Despite the advancements in our understanding, mysteries remain. For instance, scientists are still unraveling the role of magnetic fields in shaping star-forming regions. These invisible forces thread through molecular clouds, influencing how gas flows and collapses. Recent studies suggest that magnetic fields may act as a counterbalance to gravity, slowing down the collapse and affecting the size and distribution of stars. Ultimately, star-forming regions are the cosmic workshops where the building blocks of the universe come together. They remind us that even in the cold, dark reaches of space, there is activity, change, and creation. The anatomy of these regions is a testament to the intricate interplay of forces that govern the cosmos, transforming simple gas and dust into the brilliant stars that light up our night skies. In the depths of a star-forming region, as gas and dust collapse under the pull of gravity, something extraordinary begins to happen. At the heart of the dense protostar, where temperatures and pressures rise to unimaginable extremes, a phenomenon ignites that will define the star's existence: nuclear fusion. This is the moment when a cold, dark clump of material transforms into a brilliant beacon of light, marking the true birth of a star. The journey to fusion is neither quick nor straightforward. As the protostar forms from the collapsing molecular cloud, it undergoes a series of dramatic changes. At first, the core of the protostar is cool by cosmic standards, only a few thousand degrees Kelvin. But as more material from the surrounding accretion disk falls inward, it compresses the core further, causing temperatures to skyrocket. This compression is not unlike the heat generated when air is rapidly compressed, though on an infinitely larger scale. Once the core reaches about 10 million Kelvin, conditions become extreme enough for hydrogen nuclei, protons, to overcome their natural repulsion and begin fusing together. This process, known as thermonuclear fusion, is the heart of all stars. Each fusion reaction converts hydrogen into helium, releasing vast amounts of energy in the form of light and heat. This energy pushes outward, creating a delicate balance against the inward pull of gravity. Without fusion, the protostar would collapse into a dense, dark object. With fusion, it becomes a star, Fusion is one of the most efficient energy processes in the universe, though it is far from simple. The conditions required for fusion are so precise that even a slight deviation could prevent it from occurring. This is why only certain clumps within molecular clouds, those dense and massive enough, can form stars. Smaller clumps may never achieve the necessary conditions and instead form objects like brown dwarfs, which are often referred to as failed stars. The ignition of fusion transforms the protostar into what astronomers call a main sequence star, the longest and most stable phase of a star's life. Main sequence stars, including our Sun, are defined by the steady fusion of hydrogen into helium in their cores. This stability is what makes stars such reliable sources of light and energy, supporting the formation of planets and, in some cases, the development of life. Interestingly, the mass of a star determines nearly everything about its life cycle, including how it ignites and sustains fusion. Massive stars, which are at least 8 times the mass of the Sun, ignite fusion faster and burn their fuel more quickly, shining with intense luminosity but living shorter lives. Smaller stars, such as red dwarfs, fuse their hydrogen so slowly that they can persist for trillions of years, far longer than the current age of the universe. As the star settles into its main sequence phase, it begins to radiate energy outward, creating the light that illuminates the surrounding gas and dust. This light reveals the intricate structures of the star-forming region, casting shadows and highlighting the interplay of matter and energy. Infrared telescopes like the James Webb Space Telescope have captured stunning images of these moments, showing newly born stars nestled within cocoons of gas. One of the most fascinating aspects of nuclear fusion is its role in shaping the universe's chemistry. When the first stars formed, they consisted almost entirely of hydrogen and helium, the primordial elements created during the Big Bang. But as these stars burned through their fuel, they forged heavier elements like carbon, nitrogen, and oxygen through a process known as stellar nucleosynthesis. These elements, essential for planets and life, were later dispersed into space when the stars died, seeding the next generation of star-forming regions. The energy released by nuclear fusion is also what makes stars visible across vast cosmic distances. Light from stars can travel millions or even billions of years to reach us, providing a window into the universe's past. When we observe distant galaxies, we are seeing the light from stars that ignited long before Earth existed, offering a glimpse of what the cosmos looked like in its early days. Fusion also brings with it a certain inevitability. While it marks the birth of a star, it also sets the clock ticking on its eventual demise. As a star burns through its hydrogen fuel, the balance between gravity and radiation begins to shift. For massive stars, this imbalance leads to explosive deaths as supernovae, while smaller stars quietly fade into white dwarfs. Yet even in death, stars continue to shape the cosmos, spreading the elements forged in their cores far and wide. Despite its brilliance, the ignition of nuclear fusion is invisible to our eyes. The dense gas and dust surrounding young stars absorb visible light, making these early stages of stellar evolution impossible to observe directly. However, by studying the infrared radiation emitted by these regions, astronomers have been able to piece together a detailed picture of how stars ignite. These observations reveal not only the conditions necessary for fusion, but also the variations in how stars form under different cosmic circumstances. For example, stars forming in dense clusters often interact gravitationally with their neighbors, affecting their growth and evolution. In contrast, stars forming in relative isolation may experience a quieter birth, free from the disruptive influence of nearby massive stars. These differences add to the diversity of stars and star systems, shaping the galaxies they inhabit. The birth of light through nuclear fusion is one of nature's most profound transformations. It is a process that connects the microcosmic world of atomic particles to the macrocosmic grandeur of galaxies. Every star, from the smallest red dwarf to the most massive blue giant, owes its existence to this fundamental process. And in every beam of starlight that reaches our eyes, we see the legacy of a moment when gravity and physics combined to ignite the universe's most luminous creations. Stars are not born in solitude. The vast molecular clouds from which they emerge typically produce not one but thousands of stars, all forming within the same environment and roughly at the same time. These stellar siblings, bound by their shared origins, often remain gravitationally linked, creating magnificent star clusters. These cosmic communities offer a glimpse into the dynamic relationships between stars, revealing their collective stories and their profound impact on the galaxies they inhabit. Star clusters come in two primary forms: open clusters and globular clusters. Each tells a unique tale about the processes of star formation and the evolution of the universe. To explore these clusters is to step into the diverse neighborhoods of stars, each brimming with its own intrigue and wonder. Open clusters are among the youngest and most vibrant stellar groups. Found primarily in the spiral arms of galaxies, these clusters are composed of a few dozen to a few thousand stars, loosely bound by gravity. A well-known example is the Pleiades, often called the Seven Sisters, though it contains many more stars than those visible to the naked eye. The Pleiades, located about 444 light-years from Earth, glimmers in the Taurus constellation, surrounded by a faint blue reflection nebula, a testament to the cluster's youth and proximity to its birthplace. The stars in open clusters are generally hot and luminous, illuminating the surrounding gas and dust. These clusters are short-lived on cosmic timescales. Over hundreds of millions of years, gravitational interactions with nearby stars and the galaxy's tidal forces gradually disperse their members, leaving them to drift through space as solitary stars. Yet, while they exist, open clusters provide astronomers with critical insights into star formation. Because all the stars in a cluster formed at roughly the same time, studying them allows researchers to understand how stars of different masses evolve under similar conditions. On the other end of the spectrum are the ancient and enigmatic globular clusters, sprawling spheres containing hundreds of thousands or even millions of stars. These clusters are much older than their open counterparts, with ages often exceeding 10 billion years, nearly as old as the universe itself. Unlike open clusters, globular clusters are tightly bound by gravity, creating densely packed stellar environments where stars are separated by only fractions of a light year. One of the most famous globular clusters is Omega Centauri, visible from the southern hemisphere. It is a stunning sight, containing roughly 10 million stars within a region spanning just 150 light years. Observing a globular cluster like Omega Centauri is akin to peering into the distant past, as these ancient communities formed during the early days of the Milky Way. Globular clusters are remarkable for their homogeneity. Most of their stars are low and heavy elements, reflecting the chemical composition of the early universe, when elements like carbon and oxygen were far scarcer. These clusters are also home to exotic objects, including pulsars, blue stragglers, stars that appear younger and hotter than their neighbors, and occasionally black holes, created through interactions between cluster members. While open and globular clusters may seem distinct, they share common origins. Both form from the gravitational collapse of molecular clouds, though the conditions within these clouds, such as density, temperature, and composition, determine the type of cluster that emerges. The larger and denser the cloud, the more massive and enduring the resulting cluster. Star clusters do more than serve as celestial landmarks. They are vital to our understanding of stellar and galactic evolution. For instance, studying the motions of stars within clusters helps astronomers measure their masses and the gravitational forces at play. Observing how clusters interact with their host galaxies provides clues about the broader dynamics of galactic structure. In some cases, clusters even reveal evidence of galactic collisions and mergers, leaving behind tidal streams of stars that stretch across the sky. Clusters also serve as laboratories for understanding the life cycles of stars. By plotting the brightness and color of stars in a cluster, astronomers create a Hertzsprung-Russell diagram, a tool that reveals how stars evolve over time. This method has been instrumental in dating clusters, confirming that globular clusters are among the oldest structures in the universe. The role of star clusters extends beyond their scientific importance. They are also essential for shaping the galactic environment. Massive stars within clusters emit powerful stellar winds and ultraviolet radiation, sculpting their surroundings and triggering new waves of star formation. In some cases, clusters can drive the formation of superbubbles, enormous cavities in the interstellar medium filled with hot, ionized gas. Despite their significance, mysteries remain about star clusters. For example, the exact mechanisms that govern the formation of globular clusters are still debated. Are they the remnants of smaller galaxies that merged with the Milky Way billions of years ago? Or did they form directly within the galactic halo? Similarly, the dynamics of how clusters lose their stars over time, especially in the chaotic environments of galactic centers, are topics of active research. The future of star clusters is as varied as their origins. Open clusters, ephemeral by nature, will continue to dissolve into the galactic disk, their stars contributing to the Milky Way's stellar population. Globular clusters, with their robust gravitational bindings, will endure for eons, though interactions with other clusters and the galaxy itself may eventually tear them apart. What makes star clusters so fascinating is their dual role as both individual systems and components of larger cosmic structures. They remind us that the universe is not an empty void, but a connected web of matter and energy, where even the most massive stars are part of a broader narrative. To study clusters is to explore the communal life of stars, uncovering the relationships that define our cosmos. Star formation is a masterpiece of balance, orchestrated by forces both seen and unseen. While the dramatic collapse of molecular clouds and the ignition of nuclear fusion are visible events, there are two silent architects shaping these processes: dark matter and magnetic fields. These enigmatic forces influence the structure and behavior of galaxies and star-forming regions, playing a critical role in how stars and star clusters come to life. Dark matter, one of the most mysterious components of the universe, is thought to account for approximately 27% of the cosmos's total mass energy content. Unlike ordinary matter, dark matter does not emit, absorb, or reflect light, making it invisible to even the most powerful telescopes. Its presence is inferred through its gravitational effects on galaxies, clusters, and large-scale cosmic structures. Without dark matter, the story of star formation would be fundamentally different. Galaxies themselves are embedded in massive dark matter halos, which provide the gravitational framework necessary for their formation and stability. These halos are crucial for gathering the gas and dust needed to create stars. Without the gravitational scaffolding of dark matter, the early universe might never have clumped into galaxies, leaving the cosmos a dark and unstructured expanse. Within individual galaxies, dark matter's role becomes subtler, but no less important. By influencing the rotation of galaxies and the distribution of mass, dark matter helps shape the locations of molecular clouds. For instance, in spiral galaxies like the Milky Way, the dense regions within the spiral arms, prime locations for star formation, are partly governed by the gravitational effects of dark matter. Simulations show that without dark matter, these regions might dissipate or fail to reach the densities required for star formation. While dark matter provides the backbone for cosmic structure, magnetic fields act as the fine-tuned strings that guide the formation of stars within molecular clouds. These fields, though invisible to the eye, thread through galaxies and molecular clouds, influencing how gas and dust behave. Their origins remain an open question, but their presence is undeniable, detected through observations of polarized light emitted by interstellar dust. Magnetic fields are particularly significant in the early stages of star formation. As molecular clouds collapse under gravity, magnetic fields resist this compression, slowing the collapse and channeling material along field lines. This resistance is a double-edged sword. While it can delay star formation, it also prevents clouds from fragmenting too quickly, allowing for more massive stars and clusters to form. Observations from telescopes like the Atacama Large Millimeter/Submillimeter Array, ALMA, and the Planck Observatory have revealed intricate magnetic structures within star-forming regions. These observations show how magnetic fields shape the filaments of molecular clouds, directing gas flows and creating the conditions for stars to form. In regions like the pillars of creation, magnetic fields appear to act as stabilizing forces, maintaining the towering structures against the disruptive effects of stellar winds and radiation. The interplay between gravity, turbulence, and magnetic fields creates a dynamic environment in which stars are born. Magnetic fields can also influence the rotation of protostars and the formation of their accretion disks. As a collapsing cloud spins faster, magnetic fields can transfer angular momentum outward, preventing the protostar from spinning apart and ensuring the orderly formation of planetary systems. On larger scales, magnetic fields help regulate the star formation rate in galaxies. Galaxies with stronger magnetic fields often show distinct patterns in their star-forming regions, suggesting that these fields shape the distribution of molecular clouds and their ability to collapse. This regulation ensures that galaxies don't exhaust their gas supply too quickly, allowing star formation to persist over billions of years. The relationship between dark matter and magnetic fields is another intriguing aspect of cosmic evolution. While dark matter operates on vast scales, shaping the overall structure of galaxies and clusters, magnetic fields work on smaller scales, influencing individual star-forming regions. Together, they create a multi-scale framework that governs the formation and evolution of stars and clusters. One of the most exciting areas of research is the role of dark matter in the early universe. During the cosmic dark ages, before the first stars ignited, dark matter dominated the universe's gravitational dynamics. The first molecular clouds, and subsequently the first stars, likely formed in regions where dark matter was most concentrated. These dense pockets, known as dark matter halos, acted as the seeds for galaxy formation. As telescopes like the James Webb Space Telescope continue to probe deeper into the universe, they are uncovering evidence of these early structures, providing clues about how dark matter influenced the first waves of star formation. Observations of ancient galaxies show that star formation in the early universe was far more intense than it is today, likely driven by the rapid collapse of gas within dark matter halos. Despite their profound influence, both dark matter and magnetic fields remain subjects of significant mystery. The exact nature of dark matter is one of the greatest unsolved problems in physics. Is it composed of particles yet to be discovered, or does it represent a fundamental flaw in our understanding of gravity? Similarly, the origins of cosmic magnetic fields challenge current theories. Did they arise from the movement of charged particles in the early universe? Or are they remnants of processes we have yet to comprehend? The ongoing study of these forces promises to reshape our understanding of the cosmos. Future observatories like the Square Kilometre Array, SK, and the next generation of particle detectors aim to unravel these mysteries, offering insights into how the invisible forces of the universe shape the stars we see. Dark matter and magnetic fields are the unseen architects of star formation, working in concert with gravity to create the cosmic tapestry of light and life. They remind us that the universe is governed by forces far beyond human perception, weaving a complex and beautiful story that continues to unfold with every new discovery. The formation of stars is not a quiet, isolated process. Once a star is born, it begins to interact with its surroundings in profound ways, creating ripples of change across its environment. These interactions, known as stellar feedback loops, are both destructive and creative. Through their light, heat, winds, and eventual deaths, stars shape the regions around them, influencing the birth of new generations of stars and the evolution of entire galaxies. Stellar feedback starts as soon as a star ignites nuclear fusion and begins radiating energy. In massive star-forming regions like the Orion Nebula, young stars illuminate their surroundings with ultraviolet light, ionizing nearby gas and creating vast, glowing structures known as H2 regions. These regions are some of the most visually striking areas in the universe, with their colorful emissions painting the sky in shades of red, pink, and purple. Yet, behind this beauty lies a dynamic process of transformation. One of the most significant aspects of stellar feedback is stellar winds, streams of charged particles ejected from the surfaces of young, hot stars. These winds can blow away surrounding gas and dust, disrupting the molecular cloud from which the stars were born. At first glance, this might seem counterproductive to star formation, as it prevents more gas from collapsing into new stars. However, this process often creates dense shells and filaments within the cloud, compressing gas in certain areas and triggering the collapse of new cores. This phenomenon, known as triggered star formation, demonstrates the dual nature of stellar feedback. It destroys and creates simultaneously. Massive stars, those with many times the mass of our Sun, have an outsized impact on their environments. These stars emit intense ultraviolet radiation that heats nearby gas, creating high-pressure zones that can sweep through molecular clouds. Over time, this radiation carves out vast cavities in the interstellar medium, leaving behind structures like the pillars of creation in the Eagle Nebula. Within these cavities, denser regions may collapse to form new stars, while the surrounding gas dissipates into the wider galaxy. Supernova explosions are the most dramatic example of stellar feedback. When a massive star reaches the end of its life, it collapses under its own gravity, triggering a colossal explosion that ejects its outer layers into space. This explosion enriches the surrounding interstellar medium with heavy elements like carbon, oxygen, and iron, forged during the star's lifetime. These elements are essential for the formation of planets, oceans, and life itself. In this way, supernovae act as cosmic seeders, scattering the building blocks of future stars and worlds. The shock waves from supernovae also play a critical role in shaping star-forming regions. These waves compress gas as they move outward, igniting new rounds of star formation in their wake. In some cases, supernova remnants, like the famous Crab Nebula, reveal intricate webs of gas and dust, showcasing the complex interactions between dying stars and their environments. In star clusters, where stars are born in close proximity, feedback loops create particularly dynamic environments. The collective winds and radiation from hundreds or thousands of young stars can merge into powerful superbubbles, vast cavities filled with hot, ionized gas. These bubbles can span hundreds of light years, acting as both a source of turbulence and a means of dispersing material into the galaxy. The energy within superbubbles contributes to the overall dynamics of the interstellar medium, influencing where and how new stars form. Feedback from stars also shapes the larger galactic ecosystem. In spiral galaxies like the Milky Way, the energy from stellar winds, supernovae, and radiation contributes to the turbulence of the interstellar medium, maintaining the delicate balance between star formation and gas dispersion. Without this balance, galaxies might exhaust their gas supplies too quickly or fail to form stars efficiently. Feedback ensures that star formation proceeds in a regulated manner, preserving the galaxy's ability to sustain itself over billions of years. Stellar feedback loops are not limited to massive stars. Smaller stars like the Sun also contribute to their environments, though on a more modest scale. During their early stages, stars like the Sun emit intense solar winds and ultraviolet radiation that clear away gas and dust from their surroundings, shaping the development of planetary systems. Later in their lives, these stars expel their outer layers as planetary nebulae, enriching the local interstellar medium. One of the most fascinating aspects of stellar feedback is its role in regulating the size and structure of galaxies. In regions of intense star formation, such as starburst galaxies, feedback processes can become so powerful that they drive gas out of the galaxy altogether. These galactic winds are fueled by the combined effects of stellar winds, supernovae, and radiation pressure, pushing material into intergalactic space. While this might seem wasteful, it prevents the galaxy from forming stars too quickly and ensures a steady pace of evolution over cosmic time. Feedback loops also connect stars to the enigmatic realm of black holes. In galaxies with active central supermassive black holes, the energy released by accretion processes often combines with stellar feedback to regulate star formation on a galactic scale. These interactions, though not fully understood, reveal the intricate web of connections between stars, galaxies, and the universe's most extreme objects. Despite their importance, many aspects of stellar feedback remain shrouded in mystery. How exactly does feedback trigger star formation in some regions while suppressing it in others? What role do magnetic fields play in mediating these effects? And how do feedback processes vary across different types of galaxies and cosmic environments? These questions drive much of the current research in astrophysics. Modern telescopes and simulations are providing unprecedented insights into these processes. Observatories like the James Webb Space Telescope and the Very Large Telescope are capturing high-resolution images of star-forming regions, revealing the intricate structures shaped by feedback. At the same time, computational models are simulating the complex interplay of gravity, radiation, and gas dynamics, offering new perspectives on how feedback operates across scales. Stellar feedback loops are a testament to the interconnected nature of the cosmos. They show that stars are not isolated entities but active participants in a larger system, influencing and being influenced by their environments. Through their feedback, stars leave a lasting imprint on the universe, shaping the condition for the next generation of stars and ensuring the continuous evolution of galaxies. It is a cycle of creation, destruction, and renewal that has driven the cosmos for billions of years, and will continue to do so long after our own star has faded. Every star, no matter how massive or bright, is shaped by its galactic environment. Galaxies are the grand theaters of star formation, providing the raw materials, dynamic forces, and varied conditions that determine how and where stars are born. To understand the life of a star, we must zoom out and examine the broader context in which it exists, exploring the interplay between stars and the sprawling structures that host them. Galaxies are not uniform. They come in a variety of shapes, sizes, and compositions, each influencing star formation differently. Spiral galaxies, like our Milky Way, are particularly rich in star-forming regions. Their iconic spiral arms are more than just decorative. They are stellar nurseries, dense with gas and dust, where stars continuously emerge. These arms are formed by density waves, regions of heightened gravitational influence that compress gas as they rotate through the galaxy. The compression triggers the collapse of molecular clouds, initiating the process of star formation. Within these spiral arms, the conditions are ripe for creating stars. The gas is relatively cool and dense, and the gravitational influence of nearby stars and clusters provides the necessary perturbations to kickstart the collapse of gas clouds. In contrast, the central bulge of a spiral galaxy, dominated by older stars and a supermassive black hole, is a quieter region with far less star formation. The lack of cool gas and the intense gravitational forces near the galactic center create a more hostile environment for new stars to form. Elliptical galaxies, on the other hand, are largely devoid of young stars. These galaxies are dominated by older, redder stars and contain very little cool gas. The reasons for this are twofold. First, elliptical galaxies are thought to be the remnants of galactic mergers, chaotic collisions that consume much of the gas and leave little material for future star formation. Second, the supermassive black holes at the centers of elliptical galaxies often release enormous amounts of energy, heating any remaining gas and preventing it from cooling enough to collapse into stars. Dwarf galaxies present yet another perspective on the galactic environment. These smaller galaxies, often found orbiting larger ones, can be surprisingly prolific star formers given their size. In regions like the Magellanic Clouds, dwarf galaxies exhibit active star formation, fueled by their interactions with the Milky Way. These interactions, known as tidal forces, strip gas from the dwarf galaxies and trigger bursts of star formation. Dwarf galaxies also provide a glimpse into the conditions of the early universe, as their simpler structures resemble the primordial galaxies that formed billions of years ago. The influence of the galactic environment extends beyond individual galaxies to include the larger structures of the universe. Galaxies are not isolated. They are part of vast cosmic webs, connected by filaments of dark matter and intergalactic gas. In dense regions like galaxy clusters, the interactions between galaxies can have profound effects on star formation. When galaxies collide, their gas clouds can merge and compress, triggering massive starbursts. However, in the cores of these clusters, where hot gas dominates, the intense environment can strip galaxies of their gas through a process called ram pressure stripping, effectively quenching star formation. The movement of molecular clouds within a galaxy also plays a critical role in shaping star formation. Clouds located in the galactic plane are more likely to encounter other clouds, leading to collisions that compress gas and accelerate the formation of stars. In the Milky Way, this is particularly evident in the spiral arms, where the relative motions of gas clouds and density waves create ideal conditions for star-forming activity. Another fascinating aspect of the galactic environment is the influence of stellar populations on one another. In regions of active star formation, young, massive stars emit powerful winds and ultraviolet radiation, shaping the behavior of nearby gas and dust. These interactions often result in the creation of structures like bubble nebulae, where the winds from a single star have carved out a spherical cavity in the surrounding gas. On a larger scale, groups of massive stars can create superbubbles, vast voids that reshape entire regions of the galaxy. Galactic dynamics also influence the longevity of star-forming regions. In some cases, tidal interactions between galaxies can create long streams of gas that fuel star formation over extended periods. The antennae galaxies, a pair of colliding galaxies, are a vivid example of this process, with their tidal tails filled with active star-forming regions. Conversely, galaxies in isolated environments may experience slower rates of star formation, as their gas supplies are not replenished through external interactions. The location of a galaxy within the cosmic web further determines its star formation potential. Galaxies in the dense cores of clusters often show evidence of quenching, where external forces like hot gas and tidal stripping remove their ability to form stars. In contrast, galaxies on the outskirts of clusters or in more isolated regions typically maintain robust star-forming activity. The interplay between a galaxy's structure, motion, and external influences creates a rich tapestry of star formation activity. At the heart of these processes lies a simple truth: stars are both products and drivers of their environments. The energy released by stars shapes their galaxies, while the galactic environment determines the conditions for new stars to form. This feedback loop ensures that galaxies remain dynamic and evolving systems, capable of sustaining star formation over billions of years. As we peer deeper into the cosmos, telescopes like the James Webb Space Telescope are revealing the intricate connections between stars, galaxies, and the universe as a whole. Observations of distant galaxies, where star formation was more intense, provide a glimpse into the early universe and the forces that shaped the first stars and galaxies. Meanwhile, studies of nearby galaxies continue to uncover the nuanced relationships between stars and their environments, offering clues about the future of our own galaxy. The galactic environment is more than a backdrop for star formation. It is an active participant, a dynamic stage where the interplay of gravity, gas, and energy creates the stars that illuminate the cosmos. By understanding this environment, we gain a deeper appreciation for the complexity of the universe and the processes that have shaped its evolution from the very beginning. To understand the origins of the stars we see today, we must journey back in time to the early universe, when the cosmos was young, dark, and devoid of the rich complexities we now observe. This was the era when the first stars, known as Population 3 stars, were born, illuminating the universe for the very first time. Their formation marked the end of the cosmic dark ages and set the stage for the galaxies, clusters, and stars that followed. The cosmic dark ages began shortly after the Big Bang, as the universe expanded and cooled. During this time, the universe was a vast sea of neutral hydrogen and helium, the primordial elements formed during Big Bang nucleosynthesis. There were no stars, no galaxies, and no light. The cosmos was a blank canvas, its structure defined only by the subtle clumping of dark matter, which acted as a gravitational scaffold for the matter that would eventually form stars. Star formation in this early epoch was a fundamentally different process compared to today. The first molecular clouds were composed almost entirely of hydrogen and helium, lacking the heavier elements, called metals by astronomers, that are present in modern star-forming regions. These metals, forged in the cores of stars and spread across the cosmos by supernovae, play a crucial role in cooling molecular clouds and facilitating star formation. Without them, the early universe posed significant challenges for the creation of stars. Despite these challenges, the first stars formed in the densest regions of the primordial gas clouds, where gravity overcame the resistance of thermal pressure. These regions, located within the gravitational wells of dark matter halos, collapsed to create the first luminous objects. The lack of metals meant that these stars were likely far more massive than most stars today, with masses ranging from tens to hundreds of times that of the Sun. This immense mass was necessary because the cooling processes that typically allow smaller stars to form were inefficient in the metal-free environment of the early universe. These first stars were not just larger, they were also brighter and hotter than modern stars. Their intense ultraviolet radiation began the process of reionization, stripping electrons from the surrounding hydrogen and transforming the universe from a neutral to an ionized state. This epoch, known as the Epoch of Reionization, was a turning point in cosmic history, as it allowed light to travel freely across the universe for the first time. The first stars, therefore, were both creators and disruptors, shaping their surroundings in profound ways. Because of their massive sizes, the first stars burned through their nuclear fuel quickly, living only a few million years, a blink of an eye on cosmic timescales. Their deaths were spectacular, ending in supernova explosions or, in some cases, direct collapse into black holes. These explosions seeded their surroundings with the first heavy elements, enabling the formation of the next generation of stars, known as Population 2 stars. These stars, enriched by the materials produced by their predecessors, were smaller and longer-lived, and many of them still exist in the oldest regions of galaxies today. Studying the early universe and the first stars presents significant challenges. No Population 3 stars have been directly observed, as their massive sizes and short lifespans mean they disappeared long ago. However, their presence is inferred through their effects on their environments and the chemical compositions of ancient stars. For instance, the oldest stars in the Milky Way, found in globular clusters and the galactic halo, show evidence of having formed from the remnants of Population 3 stars, as they contain small amounts of heavier elements but remain relatively metal-poor. The formation of the first galaxies was closely tied to the birth of the first stars. As dark matter halos grew larger, they attracted more gas, leading to the formation of stellar systems and the early building blocks of galaxies. These proto-galaxies were chaotic and irregular, lacking the structure of the spiral and elliptical galaxies we see today. Over time, as they merged and evolved, these early galaxies laid the foundation for the larger, more organized galaxies of the modern universe. One of the most intriguing aspects of early star formation is the role of quasars, the highly luminous centers of galaxies powered by supermassive black holes. Quasars were some of the brightest objects in the early universe, and their intense radiation likely influenced nearby star-forming regions, either triggering star formation by compressing gas or suppressing it by heating the surrounding medium. The relationship between quasars and the first stars is a subject of ongoing research, as it provides insights into how the first galaxies and black holes co-evolved. Modern telescopes are beginning to unveil the secrets of this ancient era. The James Webb Space Telescope, JWST, with its unparalleled sensitivity to infrared light, is peering deeper into the universe than ever before, observing galaxies as they appeared less than a billion years after the Big Bang. These observations are providing critical data on the conditions of the early universe and the processes that led to the first stars and galaxies. Early results from JWST have already challenged existing theories, suggesting that star formation in the early universe may have been more efficient and widespread than previously thought. Simulations also play a vital role in studying the first stars. Using powerful supercomputers, scientists recreate the conditions of the early universe, modeling the behavior of gas, dark matter, and radiation to understand how the first stars formed and evolved. These simulations have revealed the likely locations of Population 3 star formation, as well as the mechanisms that allowed their massive sizes and rapid life cycles. The story of the first stars is not just about the past. It is a window into the fundamental processes that govern the universe. By studying these early objects, we learn about the interplay between gravity, gas, and radiation, as well as the origins of the elements that make up planets and life. The first stars were pioneers, lighting the way for the cosmos to evolve from a dark, formless expanse into the structured and vibrant universe we see today. The early universe was a time of transformation, marked by the birth of the first lights. These stars, though long gone, continue to influence the cosmos through their descendants and the heavy elements they produced. They remind us that even in the most challenging environments, the universe finds ways to create beauty, complexity, and light. As the universe continues its slow expansion, star formation persists, shaping galaxies and producing new sources of light. Yet, the future of star formation is tied to the evolving cosmic conditions that govern the availability of gas, the interactions between galaxies, and the influence of dark energy. What does the future hold for the creation of stars? And how will the universe's most luminous phenomena change over the coming billions and trillions of years? At present, the universe is in what astronomers call the stelliferous era, a time when star formation is at its peak. Molecular clouds and galaxies continue to collapse, fueled by the steady recycling of gas through processes like stellar feedback, galactic mergers, and accretion from intergalactic space. Spiral galaxies, like the Milky Way, are the primary engines of star formation, with their dense spiral arms acting as cosmic nurseries. However, even now, the rate of star formation is declining. This decline is largely due to the depletion of available gas, the raw material for stars. As stars form, they consume the hydrogen and helium in molecular clouds, leaving behind heavier elements and remnants like black holes, neutron stars, and white dwarfs. While stellar feedback processes recycle some of this material back into the interstellar medium, much of it is locked away in compact objects or dispersed into space, making it less accessible for future star formation. The expansion of the universe, driven by dark energy, also plays a significant role in the future of star formation. As galaxies move farther apart, the inflow of gas from intergalactic space diminishes, cutting off a crucial supply of material for forming new stars. This effect is particularly pronounced in isolated galaxies, which lack the tidal interactions and mergers that can rejuvenate star formation by compressing gas and triggering activity. Over the next few billion years, the universe will witness significant changes in the patterns of star formation. In large galaxies like the Milky Way, the central regions will likely become less active, as the available gas is either consumed or ejected by stellar winds and supermassive black hole activity. Star formation will become concentrated in the outer regions, where gas densities remain higher. However, even this activity will eventually dwindle as the galaxy's gas supply is exhausted. One of the most intriguing prospects for the future of star formation lies in galactic mergers. When galaxies collide, their gas clouds compress, triggering intense bursts of star formation. The Milky Way is on a collision course with the Andromeda Galaxy, set to occur in approximately 4.5 billion years. This cosmic dance will likely result in the creation of a new galaxy, often referred to as Milkomeda. The merger will trigger a final surge of star formation as the two galaxies combine their gas reserves. However, this phase will be short-lived on cosmic timescales, and the resulting galaxy will eventually settle into a quieter, more stable state. As the universe ages further, star formation will slow to a near halt. The remaining gas in galaxies will become increasingly diffuse, unable to reach the densities required to form stars. This transition marks the end of the stelliferous era and the beginning of a new phase in cosmic history. In the degenerate era, billions to trillions of years from now, the universe will be dominated by the remnants of stars, white dwarfs, neutron stars, and black holes. These objects will slowly cool and fade, leaving behind a dark, quiet cosmos. Star formation during this time will be exceedingly rare, occurring only in unusual circumstances, such as the collision of isolated molecular clouds or the accretion of material onto compact objects. Interestingly, some new stars could form from the remnants of old ones. In certain scenarios, white dwarfs in close binary systems could merge, reigniting fusion and creating a second-generation star. These zombie stars would shine briefly, providing a flicker of light in an otherwise dim universe. However, such events will be extraordinarily rare. The ultimate fate of star formation is closely tied to the behavior of dark energy, which drives the accelerated expansion of the universe. If dark energy remains constant, a scenario known as the cosmological constant, the universe will continue expanding forever, causing galaxies to drift apart and isolating them from one another. In this big freeze scenario, Star formation will cease entirely as galaxies become gravitationally isolated and their gas supplies dissipate. If dark energy behaves differently, either increasing in intensity or reversing, it could lead to other outcomes, such as a big rip, where the fabric of the universe is torn apart, or a big crunch, where the universe contracts back into a hot, dense state. These scenarios would profoundly alter the future of star formation, either accelerating its end or triggering a new cycle of cosmic creation. The tools of modern astronomy are already providing glimpses of the universe's star-forming future. Observatories like the James Webb Space Telescope and the Atacama Large Millimeter/Submillimeter Array are studying distant galaxies to understand how star formation has changed over cosmic time. By observing galaxies in various stages of evolution, astronomers can predict how the Milky Way and its neighbors will evolve and what the final stages of star formation might look like. Despite its eventual decline, the legacy of star formation will endure. The stars born in the present era will continue to shine for billions to trillions of years, illuminating the cosmos long after star formation itself has ceased. Red dwarfs, the longest-lived stars, could burn steadily for up to 10 trillion years, ensuring that light persists even in the far future. Star formation is one of the universe's most profound processes, transforming simple elements into complex structures and sustaining the cosmic cycle of creation and destruction. As we gaze into the future, we see not only the gradual fading of this process, but also the immense beauty and resilience of the stars and galaxies it has created. The story of star formation is not just about the past or present. It is a testament to the universe's ability to create light, even in the face of inevitable darkness. The story of star formation is as much about our technological journey as it is about the cosmic processes themselves. Over the centuries, humanity has developed ever more sophisticated tools to peer into the heavens, revealing the secrets of stellar nurseries, the birth of stars, and the evolution of galaxies. Today, we stand at the forefront of a new era in astronomy, where cutting-edge telescopes and innovative techniques are revolutionizing our understanding of how stars and star clusters come to life. One of the most transformative advancements in the study of star formation has been the advent of infrared astronomy. Stars are born shrouded in dense clouds of gas and dust, which absorb visible light and obscure these regions from traditional optical telescopes. Infrared light, however, can penetrate these veils, allowing us to peer into the heart of star-forming regions. The James Webb Space Telescope, JWST, launched in 2021, has already provided unprecedented views of stellar nurseries, unveiling intricate structures and revealing the earliest stages of star formation. JWST's infrared capabilities have given us a front-row seat to the dynamic processes within molecular clouds. Its detailed observations of regions like the Tarantula Nebula and the Carina Nebula have shown how young stars interact with their environments, shaping the gas and dust around them with powerful winds and radiation. These images are not just visually stunning. They provide critical data on the temperatures, densities, and chemical compositions of star-forming regions, offering new insights into the conditions required for star birth. In addition to JWST, ground-based observatories like the Atacama Large Millimeter/Submillimeter Array, ALMA, have revolutionized our ability to study the cold, dense regions of molecular clouds where stars are born. ALMA's ability to detect millimeter and submillimeter wavelengths allows it to map the distribution of gas and dust in unprecedented detail. By observing the spectral lines emitted by molecules like carbon monoxide, astronomers can measure the motion and temperature of gas within molecular clouds, tracing the flows that lead to star formation. One of the most exciting discoveries made possible by ALMA is the observation of protoplanetary disks, the swirling rings of gas and dust that surround young stars. These disks are not only the birthplace of planets, but also a key component of the star formation process. By studying these disks, astronomers can learn how stars gather mass and how their environments influence the formation of planetary systems. ALMA's high-resolution images of disks, such as those around the star HL Tauri, have revealed detailed structures like gaps and rings, hinting at the presence of forming planets. Another technological leap in the study of star formation has been the use of radio astronomy. Observatories like the Very Large Array, VLA, and the upcoming Square Kilometer Array, SK, are capable of detecting the faint radio emissions from molecules and ions in star-forming regions. These observations complement the data from infrared and millimeter telescopes, providing a more complete picture of the complex processes at work. The ability to observe the universe across multiple wavelengths is one of the greatest achievements of modern astronomy. By combining data from optical, infrared, millimeter, and radio telescopes, astronomers can construct detailed models of star-forming regions, tracing the journey of gas and dust from diffuse clouds to dense cores and, ultimately, to shining stars. This multi-wavelength approach has been particularly effective in studying starburst galaxies, where intense episodes of star formation light up the universe. Looking to the future, the next generation of telescopes promises to push the boundaries of our understanding even further. The Extremely Large Telescope, ELT, currently under construction in Chile, will have a primary mirror 39 meters in diameter, allowing it to resolve tiny details in distant star-forming regions. Paired with advanced adaptive optic systems, the ELT will be able to study the birth of stars and galaxies billions of light-years away, revealing how star formation has evolved over cosmic time. The Nancy Grace Roman Space Telescope, set to launch later this decade, will complement JWST by conducting wide-field surveys of the sky. Its ability to image large regions of the Milky Way and nearby galaxies will provide a comprehensive view of star-forming activity across different environments, helping astronomers understand how factors like metallicity and galactic dynamics influence the star formation process. Beyond traditional telescopes, new techniques in gravitational wave astronomy and neutrino detection are opening entirely new windows into the universe. While these methods are not yet directly tied to the study of star formation, they provide complementary insights into the broader life cycle of stars, including the violent deaths of massive stars and supernovae. These explosions, in turn, play a crucial role in triggering and enriching star-forming regions. Simulations and artificial intelligence are also becoming indispensable tools in the study of star formation. Using supercomputers, astronomers can recreate the conditions within molecular clouds, modeling the complex interplay of gravity, turbulence, magnetic fields, and feedback processes. These simulations allow researchers to test hypotheses about how stars form and evolve, providing a theoretical framework to interpret observational data. Machine learning algorithms, meanwhile, are helping to analyze the vast amounts of data generated by modern observatories, identifying patterns and correlations that might otherwise go unnoticed. Perhaps one of the most profound contributions of cutting-edge technology is its ability to inspire new questions. For example, recent observations by JWST and ALMA have revealed that star formation in the early universe may have been more efficient and widespread than previously thought, challenging existing models. Similarly, the discovery of complex organic molecules in star-forming regions raises intriguing questions about the origins of life and the conditions necessary for its development. As technology continues to advance, the pace of discovery will only accelerate. Each new instrument and technique brings us closer to answering fundamental questions about the universe. How do stars form in different environments? What role do magnetic fields and turbulence play in shaping stellar nurseries? How has star formation changed over cosmic history, and what does it tell us about the fate of the universe? The pursuit of these answers is not just a scientific endeavor. It is a celebration of humanity's curiosity and ingenuity. The tools we build to explore the cosmos reflect our relentless desire to understand the universe and our place within it. Through the lens of cutting-edge technology, we are not only unraveling the mysteries of star formation, but also forging a deeper connection to the cosmos, one discovery at a time. Molecular clouds, the sprawling regions of gas and dust that serve as the cradles of star formation, are among the most dynamic and enigmatic structures in the universe. They are not static entities but evolving systems, constantly shaped by internal and external forces. Understanding the life cycle of these clouds is crucial for unraveling the mysteries of how stars and star clusters come into existence. Their journey, from diffuse accumulations of gas to the vibrant nurseries of newborn stars, is a story of balance, turbulence, and transformation. Molecular clouds begin as interstellar clouds, diffuse regions of atomic hydrogen that pervade galaxies like the Milky Way. These clouds are often the result of gas accumulation over millions of years, driven by gravitational interactions within the galaxy. As these atomic clouds cool, their hydrogen atoms pair up to form molecular hydrogen, H2, marking the transition to a molecular cloud. The cooling process is aided by the presence of heavier elements, such as carbon and oxygen, which emit radiation as they collide and interact, carrying heat away from the gas. At this stage, the molecular cloud is vast, often spanning tens to hundreds of light years, with a mass that can reach millions of times that of the Sun. However, despite their size, these clouds are incredibly tenuous, with densities far lower than the best vacuums humans can create. Their temperatures hover near absolute zero, typically between 10 and 20 Kelvin, making them some of the coldest objects in the universe. Molecular clouds are far from uniform. They are shaped by a complex interplay of gravity, turbulence, magnetic fields, and external influences like supernova shockwaves. This interplay creates dense filaments and clumps within the cloud, which serve as the seeds for star formation. Observations from telescopes like the Atacama Large Millimeter/Submillimeter Array, ALMA, have revealed these filaments in stunning detail, showing how they thread through molecular clouds like veins, channeling gas into regions of high density. The role of turbulence in molecular clouds cannot be overstated. These clouds are in a constant state of motion, with gas swirling and colliding on various scales. Turbulence is a double-edged sword. While it can prevent gas from collapsing under its own gravity, it also creates localized regions of high density where gravitational collapse becomes possible. These regions, known as dense cores, are the precursors to stars. The process of core formation is the turning point in the life cycle of a molecular cloud. As gravity takes hold in a dense core, the material within begins to collapse inward, heating up as it compresses. This marks the birth of a protostar, the earliest stage of a star's life. The surrounding material forms an accretion disk, feeding the growing protostar and often giving rise to jets of gas that stream outward along its rotational axis. While the collapse of dense cores is the most dramatic phase of a molecular cloud's life cycle, it is far from the only outcome. Many regions within a cloud fail to reach the necessary densities for star formation and remain as diffuse gas. Over time, these uncollapsed regions are dispersed by external forces, such as stellar winds from nearby stars or the shockwaves of supernovae. In this way, the life cycle of a molecular cloud is closely tied to the broader galactic environment. The feedback processes from newly formed stars are particularly influential. As young stars ignite, they emit intense ultraviolet radiation and stellar winds, carving out cavities within the molecular cloud. This feedback can either trigger further star formation by compressing nearby gas or halt it by dispersing the cloud's material. The interplay between these opposing effects determines the ultimate fate of the molecular cloud. One of the most iconic examples of stellar feedback shaping a molecular cloud is the Orion Nebula, a region teeming with young, massive stars. The radiation from these stars has carved out a glowing cavity in the surrounding gas, creating a spectacular visual display while simultaneously influencing the next generation of star formation. Observing regions like Orion allows astronomers to witness the life cycle of molecular clouds in action, from their collapse to their eventual dispersal. Molecular clouds are also shaped by larger-scale processes within galaxies. In spiral galaxies, the density waves that create the spiral arms compress gas clouds as they move through them, triggering the formation of new molecular clouds and stars. In contrast, elliptical galaxies, which lack significant amounts of cold gas, show little evidence of ongoing molecular cloud formation, reflecting their different evolutionary paths. The life cycle of molecular clouds is not limited to individual galaxies. In interacting and merging galaxies, the tidal forces and shocks generated by the collision compress gas on a massive scale, creating vast regions of star formation. These events, known as starbursts, represent some of the most intense periods of molecular cloud activity in the universe. The Antennae galaxies, for example, showcase the dramatic effects of a galactic merger, with their overlapping regions filled with dense molecular clouds and young star clusters. As the molecular cloud disperses, its role in star formation comes to an end. The remaining gas is either incorporated into the interstellar medium, where it may eventually form new clouds, or expelled from the galaxy altogether. In some cases, the remnants of molecular clouds are detected as faint, cold dust clouds, a shadow of their former glory. Despite their transient nature, molecular clouds are critical to the ongoing evolution of galaxies. They are the engines of star formation, transforming raw material into the stars that light up the cosmos. Their dense cores produce stars of various masses, from the massive giants that burn brightly for a few million years to the small red dwarfs that will shine for trillions of years. By studying the life cycle of molecular clouds, astronomers gain insights into the processes that drive cosmic evolution on both local and universal scales. The story of molecular clouds is a testament to the delicate balance of forces that govern the universe. From their chaotic beginnings to their transformative role in star formation, these clouds embody the dynamic interplay of creation and destruction that defines the cosmos. They are reminders that even the coldest, darkest regions of space are alive with activity, shaping the stars and galaxies that fill our night skies. Galaxies are among the most magnificent structures in the universe, their spiraling arms stretching across the vastness of space like celestial pinwheels. These spiral arms are not merely decorative. They are bustling regions of intense activity, where stars and star clusters are born. Understanding the role of spiral arms in star formation offers a glimpse into the dynamic processes that shape the cosmos and sustain galaxies like our own Milky Way. Spiral arms are a defining feature of spiral galaxies, the most common type of galaxy in the universe. The Milky Way, Andromeda, and countless others owe their iconic shapes to these structures, which form as a result of density waves. Unlike the physical arms of a windmill, spiral arms are not rigid. Instead, they are regions of increased density that move through the galaxy like ripples on a pond. These density waves compress gas as they pass, triggering the formation of molecular clouds and stars. To understand how spiral arms work, it helps to imagine a galactic traffic jam. Just as cars slow down and pile up on a congested highway, gas clouds and stars accumulate in the denser regions of a galaxy's disk. This accumulation increases the likelihood of interactions between gas clouds, such as collisions and compressions, which are critical for star formation. The spiral arms, therefore, act as stellar nurseries, concentrating the raw materials needed for star birth. The density wave theory, first proposed in the 1960s, provides a framework for understanding how spiral arms maintain their structure. According to this theory, the spiral pattern is a wave of gravitational influence that moves through the galaxy at a different speed than the individual stars and gas. As gas enters the wave, it is compressed, creating the conditions for molecular clouds to form and collapse. This process ensures that the spiral arms remain regions of active star formation, even as stars and gas move through them. Within the spiral arms, the conditions for star formation are ideal. The gas is cool and dense, and the gravitational influence of the arms helps overcome the turbulence and thermal pressure that can prevent cloud collapse. These regions are often illuminated by the light of young, massive stars, which form in clusters and quickly heat the surrounding gas, creating glowing nebulae. The Carina Nebula and the Pillars of Creation are prime examples of such regions, where the interplay of light and shadow reveals the ongoing drama of star formation. The Milky Way itself is a classic example of a spiral galaxy, with four primary arms: the Perseus arm, the Sagittarius arm, the Scutum Centaurus arm, and the Normo arm. Our solar system resides in a smaller spur known as the Orion arm, located between the Perseus and Sagittarius arms. Each of these arms is home to vast numbers of molecular clouds, where new stars and star clusters are continually forming. One of the most fascinating aspects of spiral arms is their role in stellar migration. Stars are not permanently bound to the arms in which they are born. As they orbit the galactic center, stars drift in and out of the spiral arms, mixing with the galaxy's older stellar population. This migration ensures that the spiral arms remain populated with young stars, even as individual stars move away. It also explains why the spiral arms are brighter and bluer than the rest of the galaxy. Their stellar population is dominated by young, massive stars that emit large amounts of ultraviolet light. Spiral arms also play a critical role in the broader ecology of the galaxy. The feedback from newly formed stars, including stellar winds and supernovae, enriches the surrounding gas with heavy elements, creating a more chemically diverse environment for subsequent generations of stars. Over time, this enrichment transforms the galaxy, increasing the metallicity of its gas and enabling the formation of planets and complex molecules. The interaction between spiral arms and the galactic environment is another area of active research. For example, when spiral galaxies collide or interact with their neighbors, their spiral arms can become distorted or even amplified, leading to bursts of star formation. The antennae galaxies, with their intertwining spiral arms, showcase the dramatic effects of such interactions, as tidal forces compress gas and create waves of star formation. The future of spiral arms is tied to the evolution of their host galaxies. Over billions of years, as galaxies lose gas through star formation and galactic winds, their ability to sustain spiral arms diminishes. In some cases, this leads to the transformation of spiral galaxies into lenticular galaxies, which lack prominent arms and have little ongoing star formation. This transition reflects the natural life cycle of galaxies, as they consume their gas and gradually shift from active to quiescent states. The study of spiral arms has been revolutionized by modern technology. Observatories like the James Webb Space Telescope and the Atacama Large Millimeter/Submillimeter Array, ALMA, provide high-resolution images and detailed spectral data, allowing astronomers to map the distribution of gas and stars within the arms. These observations reveal the intricate structures of molecular clouds, filaments, and star clusters, shedding light on the processes that sustain star formation in these regions. Simulations and theoretical models have also deepened our understanding of spiral arms. Using supercomputers, researchers can recreate the dynamics of galaxies, exploring how spiral arms form, evolve, and interact with their environments. These models provide valuable insights into the role of dark matter, gas dynamics, and feedback processes in shaping the structure of spiral galaxies. Spiral arms are more than just features of galaxies. They are engines of creation, driving the formation of stars and enriching the cosmos with light and life. By studying these dynamic regions, we uncover the mechanisms that sustain galaxies and ensure the continuity of star formation over billions of years. They remind us that even in the vastness of the universe, patterns of order and beauty emerge, shaping the galaxies we call home. The death of a star is among the most spectacular and transformative events in the cosmos. When massive stars reach the end of their lives, they explode as supernovae, releasing immense amounts of energy and scattering their enriched materials into space. Far from being mere cosmic fireworks, supernovae play a pivotal role in shaping the universe, especially in the processes of star formation. These explosive events act as both destroyers and creators, leaving a lasting impact on their surroundings. To understand the influence of supernovae on star formation, it is essential to examine the dynamics of these explosions. A supernova occurs when a star exhausts its nuclear fuel. Without the outward pressure generated by fusion, gravity takes over, causing the core of the star to collapse. This collapse triggers a violent explosion, ejecting the star's outer layers into space at speeds of tens of thousands of kilometers per second. The resulting shockwave is not only a dramatic release of energy, but also a catalyst for transformation in the surrounding interstellar medium. The shockwaves generated by supernovae compress gas and dust in their path, creating the conditions necessary for the formation of molecular clouds. These clouds, the birthplaces of stars, are often found in regions shaped by the remnants of previous supernovae. The compression caused by a supernova shockwave can overcome the turbulence and thermal pressure that usually prevent gas clouds from collapsing under their own gravity. In this way, supernovae can directly trigger the formation of new stars, setting the stage for the next generation of stellar activity. One of the most striking examples of this process is seen in supernova remnants, the expanding shells of gas and dust left behind by these explosions. Observations of remnants like the Crab Nebula and Cassiopeia A reveal intricate structures that highlight the interaction between the shockwave and the surrounding medium. These remnants often serve as stellar nurseries, with new stars forming in the dense filaments and clumps created by the shockwave's passage. Supernovae also play a crucial role in enriching the interstellar medium with heavy elements. During the lifetimes of massive stars, fusion reactions in their cores create elements like carbon, oxygen, silicon, and iron. These elements are scattered into space during the supernova explosion, where they mix with the surrounding gas. This process, known as chemical enrichment, is essential for the formation of planets, moons, and the building blocks of life. Without the contributions of supernovae, the universe would remain a barren expanse of hydrogen and helium. The influence of supernovae extends beyond individual molecular clouds. In regions with high rates of star formation, such as spiral arms and starburst galaxies, supernovae can drive large-scale changes in the interstellar medium. Multiple supernova explosions in close proximity can create superbubbles, enormous cavities filled with hot, ionized gas. These superbubbles expand outward, sweeping up material and triggering star formation at their edges. Observations of structures like the Orion-Nas superbubble provide vivid examples of how supernovae shape entire regions of galaxies. However, the role of supernovae in star formation is not solely constructive. The energy released by a supernova can also disperse gas, halting star formation in certain regions. This dual nature, both triggering and suppressing star formation, makes supernovae a complex and dynamic force in the universe. The balance between these effects depends on factors such as the density of the surrounding medium, the proximity of other molecular clouds, and the number of supernovae occurring in a given region. Supernovae also influence the dynamics of galaxies on larger scales. In dwarf galaxies, where the gravitational pull is weaker, the energy from supernovae can drive gas out of the galaxy entirely, reducing the potential for future star formation. This process, known as galactic wind, is particularly significant in shaping the evolution of small galaxies. In larger galaxies like the Milky Way, supernovae contribute to the turbulent motions of the interstellar medium, ensuring a continuous cycle of gas mixing and redistribution. The study of supernovae has been revolutionized by modern observatories and simulations. Telescopes like the Hubble Space Telescope and the Chandra X-ray Observatory have provided detailed views of supernova remnants, capturing their intricate structures and energetic emissions. Meanwhile, instruments like the Very Large Telescope, VLT, and the James Webb Space Telescope, JWST, are revealing the chemical fingerprints of supernovae, offering insights into the elements they produce and their role in galactic enrichment. Simulations have also become a powerful tool for understanding supernovae. Using advanced computational models, researchers can recreate the explosion of a star and its impact on the surrounding medium. These simulations allow astronomers to explore scenarios that are difficult or impossible to observe directly, such as the interactions between multiple supernovae in a dense star cluster or the effects of a supernova on a nearby molecular cloud. Despite our growing understanding, many questions remain about the role of supernovae in star formation. For example, how do supernova shockwaves interact with magnetic fields and molecular clouds? What determines whether a supernova will trigger or suppress star formation in a given region? And how do the effects of supernovae vary across different types of galaxies and cosmic environments? These questions drive ongoing research, pushing the boundaries of our knowledge. The story of supernovae is one of cosmic renewal. These explosions, born from the deaths of stars, give rise to new stars, planets, and even the elements necessary for life. They remind us that in the universe, creation and destruction are deeply intertwined, each fueling the other in an endless cycle of transformation. As we continue to study these spectacular events, we uncover not only the secrets of star formation, but also the intricate connections that bind the cosmos together. Stars rarely form in isolation. The majority of stars in the universe are born as part of binary or multiple star systems, where two or more stars orbit a common center of mass. These systems play a significant role in the broader process of star formation, influencing the dynamics of molecular clouds, the evolution of individual stars, and even the development of planetary systems. Understanding the role of binary and multiple star systems in the cosmos provides valuable insights into the interconnected nature of star formation. Binary and multiple star systems begin their lives in much the same way as single stars, forming within the dense cores of molecular clouds. However, the processes that lead to the fragmentation of these cores and the formation of multiple stars are distinct and complex. As a molecular cloud collapses, turbulence and rotational motion can cause the core to break into smaller fragments, each of which forms a protostar. If these fragments remain gravitationally bound to one another, they become a binary or multiple star system. The formation of binary systems is influenced by several factors, including the initial mass and angular momentum of the molecular cloud. High angular momentum can cause the cloud to spin rapidly as it collapses, making fragmentation more likely. Magnetic fields and turbulence also play crucial roles, helping to redistribute angular momentum and shape the collapse. These interactions result in a wide variety of binary configurations, from tightly bound pairs to widely separated systems. Once a binary or multiple system forms, the stars within it influence one another's evolution in profound ways. For example, in close binary systems, the gravitational interaction between the stars can lead to mass transfer, where one star siphons material from its companion. This process can significantly alter the life cycles of both stars, often creating exotic phenomena like novae, X-ray binaries, and even type I supernovae. In some cases, the interaction between stars can prevent one from evolving normally, extending or shortening its lifespan. Binary systems also play a pivotal role in enriching the interstellar medium. When massive stars and binary systems explode as supernovae, their close proximity to a companion star can lead to unique interactions. For instance, a supernova explosion in a binary system can disrupt the orbit of the surviving star, ejecting it into space as a runaway star. These stars travel at incredible speeds and carry heavy elements to regions of the galaxy far from their birthplace, contributing to the chemical diversity of the cosmos. In addition to their impact on individual stars, binary and multiple systems influence the formation and stability of planetary systems. Planets that form around stars and binary systems experience gravitational forces from both stars, which can create complex orbital dynamics. Depending on the distance between the stars, planets may orbit one of the stars, known as S-type orbits, or both stars together, known as P-type orbits. These configurations can lead to unique planetary environments, with varying levels of light and heat as the planets move through their orbits. Interestingly, some of the most famous exoplanet discoveries have been made in binary systems. For example, the Kepler-47 system features 2 stars orbited by multiple planets, demonstrating that planetary systems can form and thrive even in the dynamic environments of binary stars. Such discoveries challenge traditional models of planet formation and suggest that the conditions for life might be more common than previously thought. Binary and multiple star systems also offer critical insights into the overall star formation process. Because these systems are so common, accounting for more than half of all stars in the Milky Way, they provide a natural laboratory for studying the interactions between stars. By observing binaries, astronomers can measure fundamental stellar properties, such as mass and radius, with unparalleled precision. This information helps refine models of stellar evolution and improve our understanding of the mechanisms that drive star formation. Advances in observational technology have been instrumental in studying binary and multiple star systems. Telescopes like the Hubble Space Telescope and ground-based observatories equipped with adaptive optics have resolved binary stars that were previously indistinguishable as single points of light. The use of spectroscopy, which analyzes the light from stars to detect their motions, has also revealed the presence of unseen companions in many systems. These techniques have expanded our knowledge of binary star populations, uncovering a wide range of configurations and characteristics. Theoretical models and simulations have further deepened our understanding of how binary and multiple systems form and evolve. By simulating the collapse of molecular clouds and the fragmentation of dense cores, researchers have identified the conditions that favor the formation of binaries and the factors that influence their separations and masses. These models also explore the long-term dynamics of binary systems, including how interactions with nearby stars and molecular clouds can alter their orbits and configurations. Despite significant progress, many mysteries remain. For example, the precise mechanisms that determine whether a collapsing core will form a single star or a binary system are still not fully understood. Similarly, the role of magnetic fields and turbulence in shaping the fragmentation process continues to be an area of active research. Answering these questions is crucial for developing a comprehensive picture of star formation. Binary and multiple star systems are more than just fascinating curiosities. They are a fundamental aspect of the cosmic tapestry. Their interactions shape the evolution of stars and galaxies, drive the enrichment of the interstellar medium, and create some of the most dramatic phenomena in the universe. By studying these systems, we uncover the intricate web of connections that defines the cosmos, revealing how stars influence one another and the environments in which they form. The prevalence and diversity of binary and multiple star systems remind us that the universe thrives on complexity. These systems challenge our understanding of star formation, offering new perspectives on how stars are born, evolve, and ultimately shape the cosmos. They are a testament to the interconnectedness of the universe, where even the most distant stars are linked by their shared origins and interactions. While most stars form in the familiar settings of spiral galaxies and molecular clouds, the universe is filled with extreme environments that push the limits of star formation. From the chaotic centers of galaxies to the hostile realms of galaxy clusters, these extraordinary conditions reveal the adaptability and resilience of the processes that create stars. Exploring star formation in such extreme environments not only broadens our understanding of stellar origins, but also highlights the diversity of the cosmos. The centers of galaxies are among the most dynamic and extreme environments in the universe. These regions are densely packed with stars, gas, and dust, all swirling around a supermassive black hole. In the Milky Way, the central region, known as the galactic center, is home to the supermassive black hole Sagittarius A, which has a mass equivalent to about 4 million suns. Despite the gravitational dominance of the central black hole, star formation persists in this turbulent environment. Observations of the galactic center reveal clusters of young, massive stars that have formed within the last few million years. These stars are often located in dense molecular clouds, such as the central molecular zone, where the gas is compressed by the intense gravitational forces and dynamic interactions of the region. Star formation near supermassive black holes is a delicate balance of forces. The powerful gravitational pull of the black hole creates immense tidal forces that can disrupt molecular clouds, making it difficult for them to collapse and form stars. At the same time, the energy released by the accretion of material onto the black hole generates intense radiation and outflows, heating the surrounding gas and potentially suppressing star formation. Yet in some cases, these same processes can trigger star formation. Shock waves from outflows and jets can compress gas, creating dense regions that collapse into stars. This dual role of the central black hole, both suppressing and encouraging star formation, highlights the complexity of these environments. The interplay between gravity, turbulence, and feedback processes creates a unique setting where stars are born despite the odds. Galaxy collisions are among the most dramatic events in the cosmos, and they provide fertile ground for intense episodes of star formation. When two galaxies collide, their gas clouds interact and compress, triggering waves of star formation known as starbursts. These events can produce stars at rates hundreds or even thousands of times greater than those in normal galaxies. The Antennae galaxies are a prime example of a starburst triggered by a galactic collision. As these two galaxies merge, their gas clouds are funneled into dense regions, where the conditions for star formation are ideal. Observations of the Antennae galaxies reveal clusters of young, massive stars, along with glowing nebulae that mark the birthplaces of new stellar generations. Starbursts are also associated with ultraluminous infrared galaxies, ULIRGs, which are characterized by their intense infrared emissions. These galaxies often result from mergers and contain massive amounts of gas and dust, which fuel both star formation and the growth of central black holes. The interplay between these processes creates some of the most luminous objects in the universe. However, starbursts are not sustainable over long timescales. The rapid consumption of gas and the feedback from massive stars and supernovae eventually quench the star formation, leaving behind a galaxy that is depleted of its star-forming material. These events, though fleeting on cosmic timescales, play a significant role in shaping the evolution of galaxies. Galaxy clusters are the largest gravitationally bound structures in the universe, containing hundreds or thousands of galaxies surrounded by hot, ionized gas, known as the intracluster medium, ICM. This environment, with temperatures reaching millions of degrees Kelvin, poses significant challenges for star formation. In the central galaxies of clusters, known as brightest cluster galaxies, BCGs, star formation can still occur despite the hostile surroundings. These galaxies often sit at the centers of large reservoirs of intracluster gas, which cools over time and condenses into dense molecular clouds. The result is the formation of stars in a setting that seems, at first glance, inhospitable. One of the most well-studied examples of star formation in a galaxy cluster is the Phoenix cluster, where the central galaxy is experiencing a massive burst of star formation. Observations reveal streams of cold gas flowing into the galaxy, fueling the creation of stars at rates far exceeding those in typical galaxies. This activity is driven by a combination of cooling flows and feedback from the central supermassive black hole, which regulates the process and prevents runaway star formation. Galaxy clusters also exhibit unique phenomena, such as jellyfish galaxies, which are named for their trailing streams of gas that resemble tentacles. These streams are created by ram pressure stripping, a process where the motion of a galaxy through the dense intracluster medium removes its gas. While this stripping can suppress star formation in the galaxy itself, the stripped gas can ignite new star formation in the trailing streams, creating stars in the cluster environment. The extreme conditions of the early universe provide another lens through which to study star formation. During the first billion years after the Big Bang, galaxies were smaller, more irregular, and filled with pristine gas composed primarily of hydrogen and helium. These galaxies experienced rapid and intense star formation, fueled by the high density of gas and the absence of heavy elements. Observations of the most distant galaxies, made possible by the James Webb Space Telescope, JWST, have revealed star-forming regions that challenge our understanding of the early universe. These galaxies often exhibit clumpy, irregular structures, reflecting their chaotic formation processes. The stars formed in these early galaxies were likely more massive and shorter-lived than those in the modern universe, contributing to the rapid enrichment of the intergalactic medium with heavy elements. Dwarf galaxies, despite their small size, are significant contributors to star formation in the universe. These galaxies often contain large amounts of gas relative to their stellar populations, making them efficient at forming stars. However, their low masses and weaker gravitational fields make them highly susceptible to feedback from supernovae and stellar winds, which can expel gas and suppress further star formation. Some dwarf galaxies exhibit bursts of star formation followed by long periods of inactivity. This feast or famine pattern is driven by the interplay between gas inflows, feedback processes, and interactions with larger galaxies. These galaxies provide a unique laboratory for studying the processes that regulate star formation in low-mass systems. The diversity of environments in which star formation occurs highlights the adaptability of the underlying processes. Whether in the dense cores of galaxies, the chaotic aftermath of collisions, or the high-energy realms of galaxy clusters, the universe finds ways to create stars. This resilience underscores the fundamental importance of star formation to the evolution of cosmic structures. By studying star formation in extreme environments, astronomers gain a deeper understanding of the forces that shape the universe. These environments, though challenging, are also the engines of cosmic creativity, producing the stars, planets, and galaxies that fill the cosmos with light and life. Though invisible to the naked eye, magnetic fields are fundamental forces shaping the universe. They thread through galaxies, star-forming regions, and molecular clouds, influencing the behavior of gas and dust at every stage of star formation. These fields, often overlooked, act as hidden architects, guiding the collapse of clouds, regulating turbulence, and shaping the structures that give rise to stars and star clusters. The origins of magnetic fields. Magnetic fields are generated through a process known as the dynamo mechanism, which occurs in electrically conducting fluids like plasmas. As charged particles move, they create magnetic fields, and these fields can amplify under certain conditions. In galaxies, the rotation of the disk and the motion of ionized gas combine to sustain large-scale magnetic fields that span tens of thousands of light years. On smaller scales, within molecular clouds and star-forming regions, these magnetic fields are often tangled and complex. The interplay between turbulence and gravity stretches and twists the magnetic field lines, creating a dynamic and evolving structure. Observations suggest that magnetic fields are present even in the densest regions of molecular clouds, where star formation occurs, though their exact origins and evolution remain active areas of research. Magnetic fields in molecular clouds. Molecular clouds, the cradles of star formation, are permeated by magnetic fields that influence their behavior in subtle but profound ways. One of the most important roles of magnetic fields is regulating the collapse of gas. As gravity pulls gas inward, magnetic fields provide resistance, slowing the collapse and preventing it from occurring too quickly. This resistance helps stabilize molecular clouds, allowing them to maintain their structure over millions of years. At the same time, magnetic fields guide the flow of gas within molecular clouds. Observations with instruments like the Atacama Large Millimeter/Submillimeter Array, ALMA, and the Planck Observatory have revealed that magnetic field lines often align with the filaments of gas in molecular clouds. These filaments are the precursors to star formation, and their alignment with magnetic fields suggests that these invisible forces play a key role in shaping the structures where stars are born. The role of magnetic fields in star formation. When a region of a molecular cloud becomes dense enough to collapse under its own gravity, magnetic fields continue to influence the process. As the gas collapses, the field lines become compressed and twisted, creating a magnetic bottleneck that can slow or even halt the collapse. This phenomenon, known as magnetic braking, redistributes angular momentum, ensuring that the gas does not spin too rapidly as it falls inward. Without this mechanism, the collapsing gas could fragment prematurely or form chaotic structures. Magnetic fields also shape the formation of accretion disks around protostars. These disks, which channel material onto the forming star, are crucial for star growth and the eventual formation of planetary systems. Magnetic fields threading through the disk can launch jets of gas that carry away excess angular momentum, allowing the disk to stabilize and continue feeding the protostar. These jets are some of the most striking features of young stars, visible as collimated streams of plasma extending for light years into space. Observing magnetic fields in action. Magnetic fields are notoriously difficult to observe directly, but astronomers have developed several techniques to infer their presence and behavior. One of the most powerful methods is the study of polarized light. When light passes through a region of space containing aligned dust grains, it becomes polarized, with its electric field aligned in a specific direction. This polarization reveals the orientation of the magnetic field in the region, providing a map of its structure. Radio and submillimeter telescopes, such as ALMA and the Sophia Observatory, have provided high-resolution maps of magnetic fields in star-forming regions. These observations show intricate patterns of field lines, often correlating with the density and motion of gas. For example, studies of the pillars of creation in the Eagle Nebula have revealed how magnetic fields guide the flow of material in these iconic structures, shaping the formation of stars within them. In addition to polarization, astronomers use the Zeeman effect, a phenomenon where magnetic fields split the spectral lines of atoms and molecules. This effect provides direct measurements of the strength and direction of magnetic fields in specific regions, offering insights into their role in shaping molecular clouds and protostars. The interaction of magnetic fields and turbulence. Turbulence, the chaotic motion of gas within molecular clouds, is another key factor in star formation, and it interacts with magnetic fields in complex ways. While turbulence tends to mix and randomize gas motions, magnetic fields can impose order, channeling the flow of gas along specific directions. This interaction creates a delicate balance, with magnetic fields acting to regulate the effects of turbulence. In some cases, turbulence can amplify magnetic fields through a process known as turbulent dynamo action. This amplification strengthens the influence of magnetic fields within molecular clouds, increasing their ability to guide gas flows and regulate collapse. The interplay between turbulence and magnetic fields is a dynamic feedback loop, shaping the evolution of molecular clouds and the stars they produce. Magnetic fields beyond molecular clouds. Magnetic fields extend their influence beyond individual star-forming regions, shaping the broader structure of galaxies and their star-forming activity. In spiral galaxies, for example, magnetic fields align with the spiral arms, guiding the motion of gas and playing a role in the formation of molecular clouds. These fields also influence the dynamics of the interstellar medium, channeling cosmic rays and regulating the flow of gas within the galaxy. On even larger scales, magnetic fields are thought to permeate the cosmic web, the vast network of filaments that connect galaxies and clusters across the universe. These fields may influence the motion of gas between galaxies, shaping the inflows and outflows that sustain star formation over cosmic time. The future of magnetic field research. Despite their importance, magnetic fields remain one of the least understood aspects of star formation. New observatories and instruments are poised to change this, providing deeper insights into the role of magnetic fields at every stage of the process. The Square Kilometer Array, SK, set to become the world's largest radio telescope, will revolutionize our ability to detect and map magnetic fields across the universe. By observing the polarization of radio waves from distant galaxies and quasars, SK will provide an unprecedented view of magnetic fields in molecular clouds, galaxies, and the cosmic web. Theoretical models and simulations are also advancing rapidly, incorporating magnetic fields into detailed simulations of molecular cloud collapse and star formation. These models reveal how magnetic fields interact with gravity, turbulence, and feedback processes, offering a more complete picture of the forces that shape the cosmos. Magnetic fields as cosmic sculptors. Magnetic fields are the quiet architects of star formation, shaping the structures and dynamics of molecular clouds, guiding the collapse of gas, and regulating the growth of protostars. Their influence extends from the smallest scales of star-forming regions to the largest structures in the universe, connecting the birth of stars to the broader cosmic environment. By unraveling the mysteries of magnetic fields, we gain a deeper understanding of the intricate processes that create stars and sustain the luminous tapestry of the universe. Star formation is not just about the quiet collapse of gas into a glowing sphere of nuclear fusion. It is also marked by stellar winds and outflows, dynamic processes that sculpt the surrounding interstellar medium, regulate star formation, and shape the early lives of stars. These forces, emanating from young and massive stars alike, create ripples across molecular clouds, influencing the birth of new stars and the evolution of galaxies. The genesis of stellar winds. Stellar winds are streams of charged particles, primarily protons, electrons, and helium nuclei, ejected from the surface of stars. These winds vary dramatically in strength and intensity, depending on the type and age of the star. For young stars, particularly massive ones, stellar winds are driven by intense radiation and the high-energy processes occurring in their outer layers. In smaller stars like the Sun, stellar winds are more modest but still significant, driven by the Sun's magnetic field and coronal activity. In the earliest stages of star formation, protostars, stars still gathering mass from their surrounding accretion disks, generate bipolar outflows, collimated jets of gas ejected along their rotational axis. These outflows are powered by the interaction between the protostar's magnetic field and the surrounding disk, funneling material outward at high speeds. Observations of young stellar objects, YSOs, using telescopes like ALMA have captured these jets in stunning detail, showing their role in clearing away excess gas and shaping the protostar's immediate environment. Stellar winds and massive stars. Massive stars, those with more than 8 times the mass of the Sun, produce some of the most powerful stellar winds in the universe. These winds are driven by the intense radiation pressure generated by the star's luminous output. As photons stream away from the star, They transfer momentum to the outer layers, accelerating particles to speeds of up to several thousand kilometers per second. This phenomenon, known as radiation-driven wind, creates a continuous outflow of material that carries away significant amounts of the star's mass over its lifetime. The winds of massive stars have far-reaching effects. In star-forming regions like the Orion Nebula, these winds carve out cavities and compress surrounding gas, creating dense shells that can collapse to form new stars. The interplay between stellar winds and the interstellar medium gives rise to structures like bubble nebulae, where the expanding shell of gas glows from the ionizing radiation of the central star. The impact on star formation. While stellar winds clear away gas and dust, they can also trigger sequential star formation. As the winds compress nearby material, they increase its density, creating conditions favorable for the collapse of molecular clouds. This feedback mechanism ensures that the death throes of one star generation contribute to the birth of another, sustaining the cycle of stellar evolution. However, the influence of stellar winds is not uniformly constructive. In some cases, particularly in regions dominated by massive stars, the combined effects of winds, radiation, and supernova explosions can disperse molecular clouds, halting star formation altogether. This dual nature, both fostering and suppressing star formation, illustrates the complexity of stellar feedback processes. Jets and outflows from young stars. Protostars and their jets are among the most visually striking phenomena in star-forming regions. These jets, composed of ionized gas, are often accompanied by shock waves that light up the surrounding material, creating structures known as Herbig-Haro objects. Observations of these objects provide a direct window into the early stages of star formation, revealing how young stars interact with their environments. The outflows from protostars play a critical role in regulating the growth of the star. By ejecting angular momentum, these jets prevent the protostar from spinning too rapidly as it accretes material. This regulation is essential for the formation of stable accretion disks and the eventual development of planetary systems. The role of stellar winds in galaxies. On a galactic scale, stellar winds contribute to the dynamics of the interstellar medium. In regions with high rates of star formation, the combined effects of winds from multiple stars can create superbubbles, vast cavities filled with hot, ionized gas. These superbubbles expand outward, sweeping up surrounding material and triggering star formation along their edges. Stellar winds also play a role in enriching the interstellar medium with heavy elements. As winds carry away material from stars, they distribute elements like carbon, oxygen, and nitrogen, produced through nuclear fusion, into the surrounding gas. This enrichment is critical for the formation of planets, complex molecules, and eventually life. The interaction with magnetic fields. Magnetic fields interact closely with stellar winds and jets, shaping their direction and intensity. For protostars, magnetic fields channel the outflows into tightly collimated jets, ensuring that the material is ejected along specific pathways. In massive stars, magnetic fields influence the structure of the wind, creating features like spirals and arcs that are visible in high-resolution images. The alignment of stellar winds with magnetic field lines can also have broader implications for star-forming regions. By redistributing material along magnetic pathways, these interactions contribute to the formation of filaments and clumps, the precursors to star formation. Observing stellar winds and outflows. Advancements in observational technology have revolutionized our ability to study stellar winds and outflows. Instruments like the Hubble Space Telescope, ALMA, and the Chandra X-ray Observatory provide high-resolution images and spectral data, revealing the composition, velocity, and temperature of these dynamic phenomena. Infrared and radio observations, in particular, are invaluable for studying outflows from protostars, which are often obscured by dust. Theoretical models and simulations complement these observations, allowing astronomers to explore the underlying physics of stellar winds. These models simulate the interaction between winds and the interstellar medium, revealing how energy and momentum are transferred across different scales. The future of stellar wind research. As new telescopes like the James Webb Space Telescope and the Square Kilometre Array come online, our understanding of stellar winds and outflows will continue to deepen. These instruments will provide unprecedented views of star-forming regions, uncovering the intricate processes that shape the early lives of stars. Meanwhile, advancements in computational power will enable more detailed simulations, bridging the gap between theoretical models and observational data. Shaping the cosmos. Stellar winds and outflows are fundamental to the life cycle of stars and the evolution of galaxies. They sculpt the environments in which stars are born, regulate the growth of young stars, and enrich the universe with the elements necessary for life. These forces, though invisible to the naked eye, are among the most powerful agents of change in the cosmos, driving the processes that create and sustain the luminous tapestry of the universe. Dwarf galaxies, the smallest and most numerous type of galaxy in the universe, are often overshadowed by their massive counterparts like the Milky Way and Andromeda. Yet, these cosmic underdogs play an outsized role in the story of star formation. Their simple structures and relatively low masses make them unique laboratories for studying how stars form under conditions vastly different from those in larger galaxies. Despite their modest size, dwarf galaxies reveal some of the most dynamic and extreme examples of stellar birth and evolution. What are dwarf galaxies? Dwarf galaxies are small, faint galaxies with stellar masses ranging from a few million to a few billion suns, far less than the hundreds of billions of stars in larger galaxies like the Milky Way. They come in various shapes and types, including dwarf spheroidal galaxies, which are typically gas-poor and quiescent, and dwarf irregular galaxies, which are rich in gas and actively forming stars. The large and small Magellanic Clouds, satellite galaxies of the Milky Way, are prime examples of gas-rich dwarf irregular galaxies. Despite their differences, all dwarf galaxies share one key characteristic: their low mass. This makes them particularly sensitive to external influences, such as interactions with larger galaxies or the effects of cosmic feedback processes. These interactions shape their star-forming activity and determine their evolutionary paths. The challenges of star formation in dwarf galaxies. Star formation in dwarf galaxies occurs under conditions that are often hostile to the process. Many dwarf galaxies have low metallicities, meaning their gas contains fewer heavy elements compared to larger galaxies. These heavy elements, produced in stars and dispersed by supernovae, are critical for cooling molecular clouds and enabling the collapse of gas into stars. Without them, the gas in dwarf galaxies has a harder time cooling to the temperatures necessary for star formation. Additionally, dwarf galaxies have weaker gravitational fields, which makes it easier for stellar winds, supernova explosions, and external tidal forces to disrupt their gas. These feedback processes can eject gas into space, quenching star formation for extended periods. However, the same processes can also trigger star formation by compressing gas in localized regions, creating dense pockets where stars can form. Starbursts in dwarf galaxies. One of the most striking phenomena in dwarf galaxies is the occurrence of starbursts, short, intense periods of star formation. Starburst activity in dwarf galaxies is often triggered by interactions with nearby galaxies or the infall of gas from the intergalactic medium. These events funnel gas into the central regions of the dwarf galaxy, creating the dense conditions necessary for rapid star formation. A well-known example is the Small Magellanic Cloud (SMC), which is experiencing active star formation fueled by its interaction with the Milky Way and the Large Magellanic Cloud. Observations of the SMC reveal clusters of young, massive stars and glowing nebulae, such as the Tarantula Nebula, one of the most active star-forming regions in the local group of galaxies. Despite their intensity, starbursts in dwarf galaxies are often short-lived, lasting only a few tens of millions of years. Once the available gas is consumed or dispersed, star formation slows or halts altogether. These cycles of activity and dormancy give dwarf galaxies their characteristic feast or famine pattern of star formation. The role of feedback in dwarf galaxies. Feedback processes are particularly pronounced in dwarf galaxies, where their low masses and shallow gravitational wells make them highly susceptible to disruption. Supernova explosions and stellar winds from massive stars can drive gas out of the galaxy, creating galactic winds that remove the raw material for future star formation. This loss of gas is especially significant in dwarf spheroidal galaxies, many of which are now gas-poor and quiescent due to past feedback events. However, feedback can also have constructive effects. The shock waves from supernovae and stellar winds can compress gas, triggering the formation of new stars in regions of enhanced density. This dual role of feedback, both suppressing and stimulating star formation, adds complexity to the evolutionary paths of dwarf galaxies. Dwarf galaxies as laboratories for early universe conditions. Dwarf galaxies provide a window into the conditions of the early universe. Their low metallicities and simple structures are thought to resemble those of the first galaxies that formed after the Big Bang. Studying star formation in dwarf galaxies helps astronomers understand how stars formed in the primordial cosmos, when heavy elements were scarce, and the universe was dominated by gas composed almost entirely of hydrogen and helium. Observations of nearby dwarf galaxies, such as those in the local group, have revealed patterns of star formation that mirror those expected in the early universe. For example, the low metallicity of these galaxies means that their stars often form in larger masses and at slower rates, similar to the predicted characteristics of population 3 stars, the first stars to form in the universe. Interactions with larger galaxies. The proximity of dwarf galaxies to larger galaxies often leads to gravitational interactions that shape their star formation. These interactions can strip gas from the dwarf galaxy through processes like tidal stripping and ram pressure stripping, effectively quenching star formation. However, they can also trigger bursts of star formation by compressing gas and creating dense, star-forming regions. The Magellanic Stream, a trail of gas connecting the Magellanic Clouds to the Milky Way, is an example of the complex interplay between dwarf galaxies and their larger neighbors. This stream, created by gravitational interactions, contains pockets of dense gas where new stars may eventually form, contributing to the ongoing cycle of star formation in the local group. The contribution of dwarf galaxies to the cosmic ecosystem. Although they are small, dwarf galaxies have a significant impact on the broader cosmic ecosystem. Their supernovae and galactic winds enrich the intergalactic medium with heavy elements, seeding the surrounding environment with the raw materials for future star formation. Over time, these processes contribute to the chemical evolution of the universe, spreading the elements necessary for the formation of planets and life. Dwarf galaxies also serve as building blocks for larger galaxies. During galactic mergers, dwarf galaxies are often absorbed into more massive systems, contributing their stars and gas to the growth of the larger galaxy. This hierarchical structure of galaxy formation highlights the importance of dwarf galaxies in the assembly of the universe's grandest structures. Observing and simulating dwarf galaxies. Advances in observational technology have revolutionized the study of dwarf galaxies. Telescopes like the Hubble Space Telescope, the James Webb Space Telescope, and ALMA have provided detailed views of these systems, revealing their star-forming regions, gas dynamics, and feedback processes. Simulations of dwarf galaxies have also become increasingly sophisticated, capturing the interplay of gravity, gas flows, and feedback that drives their evolution. The resilience of dwarf galaxies. Dwarf galaxies are a testament to the resilience of star formation under challenging conditions. Despite their low masses, limited resources, and susceptibility to disruption, these galaxies continue to form stars, enriching the universe with light and elements. By studying dwarf galaxies, we gain insights into the adaptability of star formation and the diversity of environments in which stars can thrive. The story of dwarf galaxies is one of survival and transformation. These small yet vital components of the cosmic tapestry remind us that even the most unassuming structures play an essential role in shaping the universe. Among the vast and luminous star-forming regions of the cosmos lie small, dense, and enigmatic structures known as dark clouds and Bach globules. These unassuming pockets of gas and dust, often seen as shadowy patches against the brighter backdrop of nebulae or star fields, are crucial to the process of star formation. Despite their small size, these structures serve as some of the most active and fascinating nurseries for stars, offering insights into the early stages of stellar birth. What are dark clouds and Bach globules? Dark clouds, also called dark nebulae, are dense regions of molecular gas and dust that block visible light, creating areas of opacity against the brighter surroundings. Bok globules are a subset of dark clouds, smaller, isolated pockets of gas and dust typically spanning less than a light year in diameter. They are named after astronomer Bart Bok, who first proposed that these objects were sites of star formation. These structures are composed primarily of molecular hydrogen, H2, along with trace amounts of other molecules like carbon monoxide, CO, and ammonia, NH3. The dust within these regions is made up of tiny particles of silicates, carbon, and ice, which not only obscure visible light, but also play a critical role in the cooling processes that enable star formation. The role of dark clouds in star formation. Dark clouds are the larger-scale counterparts to Bok globules, and they serve as reservoirs of raw material for star formation. These clouds, often spanning tens of light years, are the sites where gravity and turbulence create dense filaments and clumps. These filaments are the precursors to stars, and their intricate structures are shaped by the interplay of gravity, magnetic fields, and turbulence. Within these clouds, certain regions become dense enough to begin collapsing under their own gravity. This process marks the beginning of star formation, as the collapsing gas and dust form protostars surrounded by accretion disks. The presence of dark clouds is often associated with large star-forming regions, such as the Horsehead Nebula and the Barnard 68 dark cloud, which exemplify the contrast between their shadowy exteriors and the brilliant stars they eventually produce. Bok globules as stellar nurseries. Bok globules represent a more localized and isolated form of star formation. These compact structures are often found near larger star-forming regions, but their small size and high density make them ideal laboratories for studying the initial stages of starbirth. Observations have confirmed that many Bok globules contain protostars or young stellar objects, YSOs, providing direct evidence of their role in star formation. The isolation of Bok globules offers unique advantages for research. Unlike larger molecular clouds, where multiple factors and external influences complicate the picture, Bok globules present a simpler environment. This makes them valuable for studying the fundamental physics of gravitational collapse, accretion, and the formation of binary or multiple star systems. Observing dark clouds and Bok globules. Dark clouds and Bok globules are challenging to observe in visible light due to their opacity, but modern telescopes equipped to detect infrared and radio wavelengths have revolutionized their study. Infrared observatories, such as the James Webb Space Telescope and the Spitzer Space Telescope, can peer through the dust to reveal the warm glow of forming stars hidden within these regions. Radio telescopes, like the Atacama Large Millimeter/Submillimeter Array, ALMA, are particularly effective for studying the molecular gas in dark clouds and Bok globules. By detecting the spectral lines of molecules like carbon monoxide and ammonia, astronomers can map the density, temperature, and motion of gas within these structures. These observations provide critical data on how gas flows and collapses to form stars. The dynamics of collapse. The collapse of a Bok globule or a dense region within a dark cloud begins when gravity overcomes the thermal pressure and magnetic forces that resist it. This balance is delicate, and external factors like shock waves from nearby supernovae or the pressure from expanding H2 regions can trigger the collapse. As the globule collapses, it fragments into smaller cores, each of which can form one or more protostars. During this process, the infalling material heats up, creating a dense, hot core surrounded by an envelope of cooler gas and dust. Observations of Bok globules often reveal bipolar outflows and jets emanating from the forming stars, evidence of the accretion process and the interplay of magnetic fields. The role of feedback in Bok globules. Feedback processes, such as stellar winds and radiation from young stars, are particularly pronounced in the confined environments of Bok globules. These forces can disrupt the remaining gas, halting further star formation or dispersing the globule entirely. However, they can also trigger star formation in nearby regions by compressing the surrounding gas. The balance between these opposing effects determines the ultimate fate of a Bok globule. In some cases, the globule may produce a single star or a small cluster before being dispersed, while in others, It may continue forming stars until its material is exhausted. The life cycles of dark clouds and Bok globules. Dark clouds and Bok globules are transient features of the universe, with lifespans ranging from a few million to tens of millions of years. As they form stars, their material is gradually depleted, and feedback processes disperse what remains into the interstellar medium. The remnants of these structures often become part of larger molecular clouds or contribute to the diffuse gas that fills galaxies. Despite their fleeting existence, these structures play a crucial role in the cosmic cycle of matter. They concentrate and process gas, transforming diffuse interstellar material into dense, star-forming regions. The stars they produce go on to enrich the galaxy with heavy elements, continuing the cycle of creation and evolution. Insights from dark clouds and Bok globules. Studying dark clouds and Bok globules provides valuable insights into the conditions necessary for star formation. These small, dense structures exemplify the delicate interplay of forces, gravity, pressure, turbulence, and magnetic fields that govern the early stages of stellar birth. They also highlight the importance of scale, showing how even the smallest pockets of the universe can contribute to the grand tapestry of stars. By unraveling the mysteries of these shadowy regions, astronomers deepen their understanding of the processes that create light and life in the cosmos. Dark clouds and Bok globules may appear as voids in the sky, but they are, in fact, the seeds of stars, brimming with the potential to illuminate the universe. Star formation is not an isolated process. It is deeply intertwined with the evolution of galaxies. The stars that form within a galaxy shape its structure, dynamics, and chemical composition over billions of years. Conversely, the galactic environment dictates the rate, location, and efficiency of star formation. This interplay creates a feedback loop where galaxies and their stars co-evolve, influencing one another in a cosmic dance that defines the visible universe. Galaxies as star factories. Galaxies are the primary sites of star formation, acting as vast reservoirs of gas and dust from which stars are born. The diversity of galaxies, from spirals and ellipticals to dwarfs and irregulars, creates a wide range of conditions for star formation. In spiral galaxies, the dense molecular clouds in the spiral arms are the main engines of stellar creation, while in elliptical galaxies, the lack of cold gas and star-forming regions limits their ability to produce new stars. The process of star formation within a galaxy is highly dynamic. Stars form in clusters and associations, often concentrated in specific regions such as the spiral arms or galactic centers. These regions are shaped by gravitational interactions, gas flows, and the influence of dark matter halos, all of which contribute to the creation and dispersal of molecular clouds. The star formation rate and the galactic life cycle. The rate of star formation varies dramatically across galaxies and over time. In the early universe, galaxies experienced high rates of star formation, often forming hundreds of solar masses of stars per year during intense periods of activity, known as starbursts. These starbursts were driven by the abundance of gas in young galaxies, as well as interactions and mergers with other galaxies that compressed gas and triggered star formation. In contrast, modern galaxies like the Milky Way exhibit much lower star formation rates, typically forming only a few solar masses of stars per year. This decline is due to the gradual depletion of gas, the effects of feedback processes, and the reduced frequency of galactic interactions in the current epoch. The star formation rate, SFR, is a critical parameter for understanding galaxy evolution. High SFRs lead to rapid enrichment of the interstellar medium with heavy elements, while low SFRs result in slower chemical evolution. Observing SFRs across different galaxies and cosmic epochs provides insights into how galaxies grow, change, and eventually reach quiescence. The role of feedback in galaxy evolution. Stars, particularly massive ones, have a profound impact on their host galaxies. Through processes like stellar winds, radiation, and supernova explosions, they inject energy and momentum into the interstellar medium, driving turbulence and redistributing gas. This feedback can regulate star formation by preventing gas from collapsing into new stars or by compressing gas to trigger additional star formation in nearby regions. In galaxies with active galactic nuclei, AGN, feedback from supermassive black holes plays an even larger role. As material falls into the black hole, it releases enormous amounts of energy, which can heat or expel gas from the galaxy. This process, known as AGN feedback, is thought to be responsible for quenching star formation in massive galaxies, transforming them from active, star-forming systems into quiescent ellipticals. The chemical evolution of galaxies. Star formation drives the chemical evolution of galaxies by producing the heavy elements necessary for planets and life. These elements, known as metals in astronomical terms, are created through nuclear fusion in stars and distributed into the interstellar medium during supernova explosions and stellar winds. Over time, successive generations of stars enrich the galaxy, increasing its metallicity. The distribution of metals within a galaxy provides clues about its star formation history. In spiral galaxies, metallicity tends to decrease with distance from the center, reflecting the higher star formation rates and more efficient recycling of gas in the inner regions. In dwarf galaxies, metallicities are generally lower, as their lower masses make it easier for feedback processes to expel metals into the intergalactic medium. Galaxy interactions and star formation. Galaxy interactions are among the most significant drivers of star formation. When galaxies collide or pass close to one another, their gravitational forces distort their structures and compress their gas, leading to intense bursts of star formation. These interactions can create tidal tails, bridges, and other dramatic features, as seen in systems like the antennae galaxies. Mergers between galaxies can also lead to the formation of elliptical galaxies, which often exhibit little or no star formation due to the consumption or ejection of their gas during the merger. However, in the early stages of a merger, the resulting compression of gas can create some of the most intense starbursts in the universe. Star formation in the context of the cosmic web. Galaxies are not isolated. They exist within the cosmic web, a vast network of filaments and voids composed of dark matter, gas, and galaxies. The location of a galaxy within this web influences its star formation activity. Galaxies in dense environments, such as galaxy clusters, experience interactions that can strip them of gas and quench star formation. In contrast, galaxies in the filaments of the cosmic web often have access to fresh supplies of gas, sustaining their star formation over longer periods. The flow of gas into galaxies from the cosmic web is a critical component of their evolution. This inflow, known as cold accretion, provides the raw material for star formation and helps sustain galaxies in the absence of major mergers. Observations of distant galaxies have revealed streams of gas connecting them to the cosmic web, highlighting the importance of these inflows in the early universe. The transition to quiescence. Over billions of years, most galaxies transition from active star-forming systems to quiescent ones. This process, known as galactic quenching, occurs as galaxies exhaust their gas supplies or lose their ability to cool gas effectively. Feedback from supernovae, AGN, and environmental interactions all contribute to this transition. Quiescent galaxies, such as ellipticals, are dominated by older, redder stars and show little or no evidence of ongoing star formation. However, they remain valuable for studying the history of star formation, as their stellar populations preserve a record of their past activity. The future of star formation in galaxies. As the universe continues to expand, the rate of star formation will decline further. Galaxies will become increasingly isolated as the expansion of space stretches the cosmic web and cuts off the inflow of gas from intergalactic space. In this big freeze scenario, star formation will eventually cease, leaving behind a universe filled with the remnants of stars, white dwarfs, neutron stars, and black holes. Despite this distant future, the current era remains rich with star formation. By studying the interplay between stars and galaxies, astronomers are unraveling the processes that have shaped the universe for billions of years and continue to light up the cosmos. Galaxies and stars, a symbiotic relationship. The relationship between star formation and galaxy evolution is symbiotic, with each shaping the other in profound ways. Stars illuminate galaxies, while galaxies provide the environments that nurture stellar birth. Together, they create the dynamic, ever-changing universe we see today. By understanding this interplay, we gain not only a deeper appreciation for the cosmos, but also a clearer picture of our place within it. Star formation is often associated with galaxies, the bustling hubs of gas, dust, and stars that light up the universe. However, not all stars are born within these organized structures. In the vast reaches of intergalactic space, far from the gravitational pull of galaxies, stars also form, albeit under very different and often extreme conditions. These isolated regions of star formation provide a unique perspective on the adaptability of cosmic processes and the diversity of environments where stars can emerge. What is intergalactic space? Intergalactic space refers to the immense voids between galaxies, where matter is far more diffuse than within galaxies themselves. This space is not entirely empty. It is filled with a tenuous medium of gas, plasma, and dark matter, known as the intergalactic medium, IgM. While the density of this medium is incredibly low compared to the interstellar medium within galaxies, it still contains enough material to fuel occasional bouts of star formation under the right conditions. The origins of intergalactic star formation. Stars form in intergalactic space through a variety of mechanisms, most of which involve the ejection or redistribution of gas from galaxies. These processes create pockets of higher density material where star formation becomes possible. Some of the key mechanisms include tidal stripping. When galaxies interact or collide, their gravitational forces can strip gas from their outer regions, flinging it into intergalactic space. This stripped gas can coalesce into dense clumps, forming stars and even small galaxies. Ram pressure stripping. As galaxies move through the dense intracluster medium of galaxy clusters, the pressure exerted by this medium can strip gas from the galaxy. The stripped gas trails behind the galaxy, sometimes forming long streams where stars are born. Galaxy mergers. Colliding galaxies often eject gas into intergalactic space. This gas can become compressed and form stars in isolated pockets or tidal streams. Primordial gas clouds. Some intergalactic stars form in regions of pristine gas left over from the early universe. These regions, known as Lyman alpha blobs, are often found near galaxies and are thought to be remnants of the material that fueled the first generations of star formation. Star formation in tidal streams. One of the most well-studied examples of intergalactic star formation occurs in tidal streams, the elongated tails of gas and stars that form during galaxy interactions. These streams, such as those in the Magellanic Stream, provide ideal conditions for star formation. The compression of gas within the streams can create dense regions where stars are born, despite the absence of a galactic host. The Magellanic Stream, a trail of gas connecting the large and small Magellanic Clouds to the Milky Way, contains clumps of dense material that have been observed forming stars. These stars are thought to be relatively young, having formed within the last few 100 million years. Their presence highlights the ability of gas in intergalactic space to condense and ignite star formation under the right conditions. Star formation in galaxy clusters. Galaxy clusters, the densest regions of the universe, are hotspots for intergalactic star formation. In these environments, the interactions between galaxies and the intracluster medium create streams and filaments of gas where stars can form. Jellyfish galaxies, so named for their trailing streams of gas, often leave behind star-forming regions in the intracluster medium as they move through the cluster. One striking example is the Perseus cluster, where observations have revealed streams of star-forming gas extending between galaxies. These stars, forming far from any galactic nucleus, provide direct evidence of the adaptability of star formation processes in environments dominated by extreme forces. The role of dark matter in intergalactic star formation. Dark matter plays a critical role in enabling star formation in intergalactic space. While the visible gas and stars are the most apparent features, these regions are often embedded within dark matter halos, which provide the gravitational pull necessary to hold the gas together. Without the influence of dark matter, the low-density gas in intergalactic space would likely disperse before it could form stars. In some cases, these dark matter halos may represent the remnants of dwarf galaxies that were stripped of their stars and gas during interactions with larger galaxies. The remaining halos act as gravitational wells, collecting gas from the surrounding medium and fostering isolated star formation. Observing intergalactic star formation. Detecting stars in intergalactic space is challenging due to their isolation and faintness. However, advances in observational technology have made it possible to identify these stellar populations. Telescopes like the Hubble Space Telescope and the James Webb Space Telescope are capable of detecting the faint light of stars and star-forming regions far from galaxies. One key method for identifying intergalactic star formation is the study of ultraviolet and hydrogen alpha emissions, which indicate the presence of young, hot stars. These observations often reveal clumps of stars and tidal streams, intracluster filaments, and other intergalactic structures. The importance of intergalactic star formation. Although intergalactic star formation is relatively rare compared to the activity within galaxies, it provides valuable insights into the broader processes that govern the universe. These isolated regions serve as natural laboratories for studying star formation in extreme conditions, where the lack of a galactic environment simplifies the interactions at play. Intergalactic star formation also highlights the interconnectedness of the cosmic web. The stars born in these regions contribute to the enrichment of the intergalactic medium, spreading heavy elements that influence the evolution of galaxies and future star formation. The future of intergalactic stars. As the universe continues to expand, intergalactic star formation is expected to decline. The increasing isolation of galaxies and the depletion of gas in the intergalactic medium will limit the conditions necessary for star birth. However, the stars that form in these environments will continue to illuminate the cosmos for billions of years, serving as a testament to the resilience of star formation in even the most unlikely settings. A testament to cosmic adaptability. The existence of stars in intergalactic space challenges traditional notions of where and how stars are born. These solitary regions of star formation remind us that the cosmos is a dynamic and interconnected system, capable of creating light in the most unexpected places. By studying these stars, we gain a deeper appreciation for the diversity of the universe and the processes that shape it. The early universe was a dark, featureless expanse following the Big Bang. This epoch, known as the Cosmic Dark Ages, persisted until the emergence of the first stars and galaxies, which began a transformative period called cosmic reionization. During this era, the light from early star formation reionized the neutral hydrogen that filled the universe, making it transparent to light and shaping the cosmos as we observe it today. Star formation played a pivotal role in this monumental transition, serving as the primary driver of reionization and the illumination of the universe. The Cosmic Dark Ages. In the first few 100,000 years after the Big Bang, the universe was filled with a hot plasma of protons and electrons. As the universe expanded and cooled, these particles combined to form neutral hydrogen atoms, creating an opaque fog that blocked the passage of light. This marked the beginning of the Cosmic Dark Ages, a period devoid of stars, galaxies, or any sources of visible light. During this time, small fluctuations in the density of matter began to grow under the influence of gravity, forming the first dark matter halos. These halos attracted gas, creating the conditions necessary for the first stars to form. The universe's first light emerged from these primordial stars, initiating the end of the Cosmic Dark Ages and the start of the reionization epoch. The first stars and their light. The first stars, known as Population 3 stars, were unlike any stars that exist today. Formed from the pristine hydrogen and helium created in the Big Bang, these stars were massive, luminous, and short-lived. They emitted intense ultraviolet radiation, capable of ionizing the surrounding hydrogen gas. As these stars ignited, their radiation created expanding bubbles of ionized hydrogen around them. These bubbles eventually merged, transforming the universe from a neutral to an ionized state. Observations of the cosmic microwave background (CMB) and the distribution of distant galaxies provide indirect evidence of this process, revealing the timeline and extent of reionization. Star formation in early galaxies. While Population 3 stars played a critical role in initiating reionization, the bulk of the process was driven by the first galaxies. These galaxies, formed within dark matter halos, contain clusters of young, hot stars that emitted copious amounts of ultraviolet light. This radiation further ionized the surrounding hydrogen, accelerating the reionization process. Early galaxies were small and irregular, with high star formation rates relative to their masses. Their gas reservoirs, though limited, were rapidly converted into stars, creating intense bursts of light. Observations of high redshift galaxies using the Hubble Space Telescope and James Webb Space Telescope have revealed populations of such galaxies, providing insights into their role in reionization. The role of stellar feedback. The process of reionization was shaped not only by the light emitted by stars, but also by the feedback processes associated with star formation. Supernova explosions and stellar winds from massive stars created shockwaves that compressed gas, triggering further star formation in some regions while dispersing gas in others. This feedback helped regulate the pace of star formation in early galaxies, balancing the competing forces of gravitational collapse and gas dispersal. However, it also limited the ability of smaller galaxies to sustain star formation over long periods, as their lower gravitational binding energy made them more susceptible to feedback effects. Reionization and the intergalactic medium. The transition from a neutral to an ionized universe had profound effects on the intergalactic medium, IGM. As the IGM became ionized, it became transparent to ultraviolet and visible light, allowing photons to travel freely across the cosmos. This transparency is what enables astronomers to observe distant galaxies and quasars, peering back billions of years to study the early universe. Reionization also influenced the thermal history of the universe. The ionization of hydrogen released heat, raising the temperature of the IGM and affecting the formation of subsequent generations of stars and galaxies. The higher temperatures inhibited the collapse of small gas clouds, suppressing the formation of low-mass galaxies. Observing reionization today. Although the epoch of reionization occurred billions of years ago, its effects are still observable in the modern universe. One of the key pieces of evidence for reionization comes from the Gunn-Peterson trough, a feature seen in the spectra of distant quasars. This trough, caused by the absorption of light by neutral hydrogen, disappears in regions where the hydrogen is fully ionized, providing a marker for the extent of reionization. Additionally, the cosmic microwave background (CMB) contains imprints of reionization. Polarization measurements of the CMB, made by observatories like the Planck satellite, reveal the effects of free electrons scattering light during the reionization epoch. These observations help constrain the timing and duration of reionization, suggesting that it began about 400 million years after the Big Bang and was largely complete by 1 billion years. Challenges and ongoing research. Despite significant progress, many aspects of reionization remain poorly understood. One of the key questions is the role of different sources of ionizing radiation. While early stars and galaxies are thought to be the primary contributors, other sources, such as quasars and active galactic nuclei, AGN, may have played a role, particularly in the later stages of reionization. Another challenge is understanding the escape of ionizing photons from galaxies. The dense gas and dust within galaxies absorb much of the ultraviolet radiation produced by stars, limiting its ability to ionize the IGM. Determining the fraction of photons that escape, known as the escape fraction, is critical for modeling the reionization process. The legacy of reionization. Reionization was a transformative epoch that reshaped the universe, enabling light to travel freely and setting the stage for the formation of large-scale cosmic structures. It marked the end of the cosmic dark ages and the beginning of the luminous universe we see today. By studying reionization, astronomers not only uncover the origins of the first stars and galaxies, but also gain insights into the processes that continue to shape the cosmos. The light from early star formation illuminates not just the universe, but also the pathways of discovery that connect us to its distant past. Star clusters are among the most striking and dynamic structures in the universe, containing groups of stars that form from the same molecular cloud. These clusters, bound together by gravity, are essential laboratories for studying stellar evolution, dynamics, and the chemical processes that shape galaxies. The life cycle of star clusters, from their formation to their eventual dispersal, reveals the intricate interplay of forces that govern the cosmos. The formation of star clusters. Star clusters form within the dense regions of molecular clouds, where gravity overcomes turbulence and magnetic pressure, causing the gas to collapse. These regions fragment into smaller cores, each of which gives rise to a protostar. In areas of high density, such as the filaments of molecular clouds, multiple stars form in close proximity, creating clusters. The majority of stars in the universe are born in clusters. These clusters come in two main types: open clusters, young, loosely bound groups of stars that typically contain a few dozen to a few thousand members. Examples include the Pleiades and the Hyades. Globular clusters, ancient, tightly bound groups of stars that can contain hundreds of thousands to millions of stars. These clusters are often found in the halos of galaxies and represent some of the oldest structures in the universe. During the early stages of formation, star clusters are embedded in the remnants of their parent molecular clouds. Radiation and stellar winds from massive stars in the cluster quickly disperse the surrounding gas, revealing the stars within. This phase, known as the embedded cluster phase, lasts only a few million years and is critical for shaping the cluster's long-term structure. The role of stellar feedback. Stellar feedback processes, including radiation, stellar winds, and supernova explosions, play a pivotal role in the early evolution of star clusters. These forces can disrupt the surrounding molecular cloud, halting further star formation and determining the fraction of gas that remains bound to the cluster. The removal of gas by feedback processes often leads to the loss of gravitational binding, causing some stars to escape the cluster. This process, known as infant mortality, is particularly significant in open clusters, where only a small fraction of the initial stars remain gravitationally bound after the first few million years. The evolution of open clusters. Open clusters are relatively short-lived compared to their globular counterparts. Over tens to hundreds of millions of years, interactions with nearby stars, galactic tides, and internal dynamics cause these clusters to gradually lose members. The stars that remain bound form a more stable core, but even this core disperses over time, leaving behind a population of stars that drift through the galaxy as part of the galactic field population. Despite their transient nature, open clusters provide valuable insights into stellar evolution. Because all the stars in a cluster formed at roughly the same time and from the same material, they serve as a natural laboratory for studying how stars of different masses evolve under similar conditions. This makes open clusters critical for calibrating models of stellar life cycles. The long-term stability of globular clusters. Globular clusters, in contrast to open clusters, are extraordinarily long-lived. These dense, spherical groups of stars are tightly bound by gravity, making them resilient to external forces. Many globular clusters in the Milky Way are over 10 billion years old, providing a window into the conditions of the early universe. The stability of globular clusters is due in part to their high stellar densities and low metallicities, which reduce the effects of stellar winds and feedback processes. However, they are not immune to change. Over time, interactions between stars within the cluster, known as two-body relaxation, cause the redistribution of energy and lead to the gradual loss of stars. Some globular clusters also experience core collapse, a process in which the central regions become increasingly dense while the outer layers expand. This creates a dynamic, ever-changing structure that reveals the complex interplay of gravity, energy transfer, and stellar evolution. Star clusters and galactic evolution. Star clusters are not isolated. They interact with their galactic environments in profound ways. As they orbit the galactic center, clusters experience tidal forces that can strip away stars, particularly from their outer regions. These interactions create tidal streams, elongated trails of stars that trace the past orbits of the cluster. Observations of these streams provide valuable information about the gravitational potential of the galaxy and the distribution of dark matter. Clusters also play a role in the chemical evolution of galaxies. The stars within clusters synthesize heavy elements through nuclear fusion and release them into the interstellar medium during supernova explosions and stellar winds. This enrichment contributes to the formation of subsequent generations of stars and planets, shaping the chemical makeup of the galaxy. The dissolution of star clusters. The final stage in the life cycle of a star cluster is its dissolution. For open clusters, this process occurs relatively quickly, often within a few 100 million years. For globular clusters, dissolution can take billions of years, driven by a combination of internal dynamics, tidal interactions, and gravitational encounters with other clusters and stars. As a cluster dissolves, its stars become part of the galactic field population, contributing to the overall stellar distribution within the galaxy. In some cases, the remnants of dissolved clusters can be traced through their shared motions and chemical compositions, known as stellar streams. Observing star clusters. Modern telescopes and instruments have revolutionized the study of star clusters. The Hubble Space Telescope has captured detailed images of globular clusters, revealing their dense cores and intricate structures. Infrared observatories like the James Webb Space Telescope have provided new views of embedded clusters, peering through the dust that obscures their early stages of formation. Spectroscopic studies of star clusters allow astronomers to determine the chemical compositions, ages, and velocities of their stars. These observations provide critical data for understanding the history of star formation, the evolution of galaxies, and the processes that shape stellar populations. The legacy of star clusters. Star clusters are more than just collections of stars. They are key pieces of the cosmic puzzle. By tracing their life cycles, astronomers gain insights into the processes that govern star formation, stellar evolution, and the dynamics of galaxies. They also serve as reminders of the interconnected nature of the universe, where stars, clusters, and galaxies evolve together in a grand cosmic symphony. From their birth in the dense cores of molecular clouds to their dissolution into the galactic field, star clusters tell the story of the universe's ongoing evolution. They are celestial archives, preserving the history of their environments and the forces that shaped them. By studying these clusters, we uncover not only the origins of stars, but also the processes that connect them to the broader universe. In recent years, the detection of gravitational waves has opened an entirely new window into the universe. These ripples in space-time, predicted by Albert Einstein's theory of general relativity, are produced by massive cosmic events, such as the mergers of black holes and neutron stars. While gravitational waves are often associated with cataclysmic events, they also have profound implications for understanding star formation and the life cycle of stars. By studying these waves, astronomers can uncover hidden aspects of stellar evolution, binary systems, and the environments where stars form and die. What are gravitational waves? Gravitational waves are disturbances in the fabric of space-time caused by the acceleration of massive objects. When two compact objects, such as black holes or neutron stars, spiral toward each other and merge, they release enormous amounts of energy in the form of gravitational waves. These waves travel across the universe at the speed of light, carrying information about the events that created them. Gravitational waves are incredibly faint, making their detection a formidable challenge. It was only in 2015 that the Laser Interferometer Gravitational Wave Observatory, LIGO, made the first direct detection of gravitational waves, opening a new era in astrophysics. Since then, observatories like LIGO and Virgo have detected dozens of events, providing valuable insights into the universe's most extreme phenomena. Gravitational waves and star formation. Gravitational waves are not directly involved in the process of star formation, but they offer critical insights into the final stages of stellar evolution and the environments where stars form. Many of the events that produce gravitational waves, such as black hole mergers and neutron star collisions, originate in regions of active or past star formation. These detections allow astronomers to trace the evolutionary pathways of stars, particularly in binary systems, which play a crucial role in producing compact objects. By studying the population of merging binaries, researchers can infer the conditions under which they formed, shedding light on the dynamics of star-forming regions and the influence of stellar feedback. Binary star systems and gravitational waves. Binary star systems are among the most common configurations for stars, and their interactions can lead to some of the most dramatic events in the universe. When the massive stars in a binary system exhaust their nuclear fuel, they collapse into black holes or neutron stars. Over time, the pair may spiral inward due to the loss of energy through gravitational wave emission. eventually merging in a spectacular event that produces a burst of gravitational waves. The detection of such events provides direct evidence of the end stages of stellar evolution. By analyzing the properties of the merging objects, such as their masses, spins, and orbital dynamics, astronomers can reconstruct their histories. These histories, in turn, reveal information about the star-forming environments that gave rise to the binary systems, including the density, metallicity, and dynamics of the molecular clouds where the stars were born. Gravitational waves as probes of star-forming regions. Gravitational waves can also serve as indirect probes of star-forming regions. For example, dense stellar environments like globular clusters and young star clusters are thought to be fertile grounds for the formation of compact binaries. In these regions, close encounters between stars can lead to the formation of tight binary systems that eventually merge. The detection of gravitational waves from such systems provides evidence of the role of cluster dynamics in shaping stellar evolution. By comparing the rates and characteristics of mergers in different environments, astronomers can test models of star cluster evolution and the influence of factors like metallicity and stellar density on binary formation. Neutron star mergers and the origins of heavy elements. One of the most exciting discoveries in gravitational wave astronomy is the connection between neutron star mergers and the production of heavy elements. When two neutron stars collide, they eject material that undergoes rapid neutron capture, our process, a process that produces elements like gold, platinum, and uranium. This discovery confirmed that neutron star mergers are a significant source of heavy elements in the universe. The link between gravitational waves and nucleosynthesis highlights the interconnected nature of star formation and cosmic chemistry. The stars that form in molecular clouds eventually enrich the universe with heavy elements through processes like supernovae and neutron star mergers. These elements then become part of the next generation of stars, planets, and even life. Gravitational waves and the cosmic web. Gravitational wave events can also provide insights into the large-scale structure of the universe. The locations of merging binaries, mapped across cosmic time, reveal patterns of star formation and galaxy evolution. By studying these distributions, astronomers can trace the growth of the cosmic web and the role of star formation in shaping the universe's structure. Future prospects for gravitational wave astronomy. The field of gravitational wave astronomy is still in its infancy, but upcoming advancements promise to revolutionize our understanding of star formation and stellar evolution. Next-generation observatories like the Einstein Telescope and the Laser Interferometer Space Antenna, LISA, will be sensitive to a broader range of gravitational wave frequencies, allowing the detection of new types of events and probing deeper into the universe's history. LISA, in particular, will focus on low-frequency gravitational waves, providing insights into the mergers of supermassive black holes and the dynamics of binary systems in distant galaxies. These observations will connect the final stages of stellar evolution to the environments where stars formed billions of years ago. The interconnected story of stars and waves. Gravitational waves are the echoes of some of the most extreme processes in the universe, and their detection has expanded our understanding of the life cycle of stars. They link the birthplaces of stars to their dramatic deaths, revealing the intricate pathways that stars take through their lives. By studying these waves, astronomers gain a new perspective on the forces that shape the universe, from the smallest molecular clouds to the largest structures in the cosmos. As the field of gravitational wave astronomy continues to grow, it will uncover even more connections between star formation, stellar evolution, and the dynamics of the universe. These discoveries will deepen our appreciation for the complexity and beauty of the cosmos, where even the invisible ripples of space-time hold the keys to understanding our origins. The birth of stars occurs in the hidden depths of molecular clouds, shrouded by gas and dust that obscure visible light. To fully understand the processes of star formation, astronomers must turn to the entire electromagnetic spectrum, from high-energy gamma rays to low-frequency radio waves. Each part of the spectrum provides unique insights, revealing different aspects of the star-forming process and the environments where stars are born. By piecing together observations across multiple wavelengths, astronomers construct a comprehensive picture of stellar nurseries and their dynamic evolution. Visible light. the tip of the iceberg. Visible light, the portion of the electromagnetic spectrum that the human eye can detect, offers some of the most iconic views of star-forming regions. Images from telescopes like the Hubble Space Telescope showcase glowing nebulae, illuminated by the intense radiation of young, massive stars. These regions, such as the Orion Nebula or the Carina Nebula, provide stunning examples of the interplay between light, gas, and dust. However, visible light is limited in its ability to penetrate the dense molecular clouds where star formation begins. Dust in these regions scatters and absorbs visible light, obscuring the early stages of stellar birth. To see beyond this veil, astronomers must rely on other wavelengths. Infrared light, peering through the dust. Infrared light is a powerful tool for studying star formation, as it can pass through dust that blocks visible light. Young stars and protostars, which are often deeply embedded in molecular clouds, emit strongly in the infrared, making this wavelength ideal for observing the early stages of star formation. The James Webb Space Telescope, JWST, has revolutionized infrared astronomy, providing high-resolution images of star-forming regions that were previously hidden. Observations from JWST have revealed intricate structures within molecular clouds, including filaments, clumps, and protostellar jets. These details offer clues about how gas flows within clouds and how gravitational collapse gives rise to stars. Infrared observations also detect the warm dust surrounding protostars, which glows at these wavelengths. This allows astronomers to measure the mass and temperature of the material in accretion disks, shedding light on the processes that govern the growth of young stars and the formation of planetary systems. Radio waves, mapping molecular gas. Radio waves, the longest wavelengths in the electromagnetic spectrum, are crucial for studying the cold molecular gas that fuels star formation. Molecules like carbon monoxide (CO), ammonia (NH3), and water (H2O) emit radio waves as they rotate and vibrate, providing a means to trace the distribution and motion of gas within molecular clouds. The Atacama Large Millimeter/Submillimeter Array, ALMA, is one of the most advanced radio observatories, capable of mapping molecular clouds in exquisite detail. ALMA's observations have revealed the filamentary structures that pervade star-forming regions, showing how gas flows along these filaments toward dense cores where stars form. These studies also measure the velocity of gas within clouds, helping to quantify the role of turbulence and gravity in star formation. Radio astronomy is also critical for studying masers, which are naturally occurring amplifiers of microwave radiation found in star-forming regions. Masers provide high-resolution information about the motion of gas and the magnetic fields within molecular clouds. Submillimeter and far infrared, cold dust and early stages. The submillimeter and far infrared regions of the spectrum are particularly sensitive to the cold dust in molecular clouds. Dust grains absorb starlight and re-emitted at these wavelengths, making submillimeter observations ideal for studying regions that are too cold and dense to be visible in other parts of the spectrum. The Herschel Space Observatory, which operated from 2009 to 2013, provided groundbreaking views of cold star-forming regions, revealing networks of filaments and clumps. These observations showed that star formation often begins in dense filaments, where gravitational collapse creates cores that eventually ignite nuclear fusion. Ultraviolet light, the influence of massive stars. Massive stars, despite their short lifespans, have a profound impact on their surroundings. Their intense ultraviolet, UV, radiation ionizes the gas in molecular clouds, creating glowing regions known as H2 regions. Observing these regions in UV light reveals the extent of ionization and provides insights into the feedback processes that shape star-forming environments. The Galaxy Evolution Explorer GALEX was a dedicated ultraviolet space telescope that mapped UV emissions from star-forming regions across the Milky Way and beyond. Its observations showed how clusters of massive stars influence their environments, triggering or suppressing star formation in nearby regions. X-rays and gamma rays. High-energy phenomena. X-rays and gamma rays, the highest energy parts of the electromagnetic spectrum, are produced in the most extreme environments of star-forming regions. Protostars often emit X-rays due to the high-energy processes occurring in their magnetic fields and accretion disks. These emissions can heat surrounding gas, influencing the dynamics of the molecular cloud. Gamma rays are rarer in star-forming regions, but can be produced by interactions between cosmic rays and molecular gas. Observing these emissions provides insights into the role of cosmic rays in heating and ionizing gas, which can affect the chemistry of star-forming clouds. The Chandra X-ray Observatory and the Fermi Gamma Ray Space Telescope have provided valuable data on these high-energy processes, helping astronomers understand the energetic environments where stars are born. Multi-wavelength synergy. The most complete understanding of star formation comes from combining data across the electromagnetic spectrum. Each wavelength probes a different aspect of the star-forming process, from the cold molecular gas traced by radio waves to the hot, ionized gas revealed by ultraviolet and X-ray observations. By integrating these perspectives, astronomers create a holistic view of how stars form and evolve. For example, observations of the Orion Nebula across multiple wavelengths reveal a rich tapestry of processes. Visible light shows the glowing gas ionized by massive stars. Infrared uncovers embedded protostars. Radio maps the molecular clouds, and X-rays highlight the energetic outflows from young stars. The future of multi-wavelength astronomy. Advances in technology are continuously expanding the capabilities of multi-wavelength astronomy. Upcoming facilities like the Square Kilometer Array, SK, and the Next Generation Very Large Array, NGVLA, will provide unprecedented views of molecular gas and magnetic fields. Meanwhile, future space missions, such as the Nancy Grace Roman Space Telescope, will complement existing observatories by providing large-scale surveys of star-forming regions. These new tools will deepen our understanding of the star formation process, revealing the intricate interactions between gas, dust, and radiation that give rise to stars. They will also help answer long-standing questions about the conditions necessary for star formation and the factors that influence its efficiency. Illuminating the hidden universe. Star formation is a complex, multifaceted process, and the electromagnetic spectrum provides the key to unlocking its secrets. By observing stellar nurseries across all wavelengths, astronomers gain a deeper appreciation for the beauty and complexity of the universe. Each part of the spectrum illuminates a different aspect of the story, from the cold beginnings of molecular clouds to the fiery radiance of newborn stars. Together, they weave a narrative of creation that spans the cosmos, connecting the smallest dust grains to the brightest stars. If you like the video, don't forget to subscribe to the channel. This helps my work a lot and shows me that you are interested in me continuing to produce more videos.